Imagine looking deep into space, so far that you're seeing the universe as it was billions of years ago. The further you look, the closer you get to the very beginning of time itself. And then, suddenly, you see something that shouldn't be there. A bright, mysterious object shining across the cosmos, so powerful that it outshines entire galaxies. This is a quasar. But where did the very first ones come from? How did they form in a universe that was still young and chaotic? And why are they still one of the biggest mysteries in astronomy today? To understand quasars, we have to go back. Way back. Back to when the universe was still in its infancy, when stars were just starting to form, and the first galaxies were beginning to take shape. This was a time when everything was different. The universe was smaller, denser, and hotter. There were no planets, no complex structures, just an expanding sea of gas and radiation. And yet, in the middle of all that chaos, something happened. Massive black holes started to form, devouring matter and unleashing energy on a scale we can barely comprehend. These objects became the first quasars, blazing beacons in a dark, early universe. But how did they form so quickly? That's the big mystery. According to what we know about black holes, they take time to grow. They start small and accumulate mass slowly as they pull in gas and dust. Yet the first quasars we've discovered are already incredibly massive, billions of times the mass of the Sun, just a few 100 million years after the Big Bang. That doesn't make sense. It shouldn't be possible for black holes to grow that fast. And yet they did. Something had to have supercharged their growth. Some unknown process must have allowed these black holes to skip the slow growth phase and become monsters almost immediately. One theory is that these black holes didn't form the way we expect. Instead of starting as small collapsed stars and growing over time, they might have been born big. Imagine a cloud of gas so dense, so massive, that instead of breaking apart to form stars, it just collapses directly into a black hole. No waiting, no slow buildup, just instant gravitational chaos. If that happened, these black holes could have started out much larger than we thought possible, giving them a head start in the race to become quasars. But if that's true, where did these enormous gas clouds come from? That's another mystery. The early universe was full of hydrogen and helium, the simplest elements, but it wasn't evenly distributed. Some regions had more gas than others, and some may have been so dense that they collapsed directly into black holes. But there's another problem. If these gas clouds were that dense, they should have created massive stars first. So why didn't they? What was different about these regions of space that allowed black holes to form instead of stars? Another possibility is that early black holes were just a lot better at feeding. Normally, black holes grow by pulling in matter from a surrounding disk of gas. But there's a limit to how fast they can do this. If they pull in too much gas too quickly, the radiation they release pushes material away, slowing down their growth. But what if these early black holes somehow bypassed that limit? What if, instead of being surrounded by a thin disk of gas, they were buried inside massive clouds of material that kept feeding them nonstop? That could have allowed them to grow much faster than we thought possible. And then there's another, even stranger idea. What if the laws of physics were just a little different back then? We assume that the rules of the universe have always been the same, but what if that's not true? What if, in the early universe, black holes could form and grow under conditions that don't exist anymore? If that's the case, then these first quasars could be relics of a universe that worked in a way we don't fully understand. But here's where things get even more puzzling. We've found a lot of these early quasars, and they all seem to have supermassive black holes at their centers. But they also seem to be sitting inside galaxies that are already surprisingly well-formed. That's weird because, according to what we know, galaxies should take time to evolve. They should start as small clumps of stars and gradually merge together to become the massive galaxies we see today. But if these quasars already have large, structured galaxies around them, that means galaxy formation was happening way faster than we thought. So now we have two mysteries instead of one. Not only do we have black holes that are growing too fast, but we also have galaxies that are forming too quickly. Did the presence of these black holes somehow accelerate galaxy formation? Or was there something else happening in the early universe that we haven't discovered yet? Scientists have been searching for answers by looking for the very first quasars ever formed. The idea is simple: if we can find the oldest quasars, we can see how they started. But that's easier said than done. These objects are incredibly far away, and their light has been traveling for billions of years to reach us. The further we look, the fainter they become. And there's another problem. The further we look back in time, the more the universe itself gets in the way. Intergalactic gas absorbs some of the light from these quasars, making them even harder to detect. But despite these challenges, astronomers have made some incredible discoveries. Using powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope, they've managed to find quasars from when the universe was less than 1 billion years old. And these objects are already huge. Some of them have black holes billions of times the mass of the Sun, meaning they must have formed incredibly fast. One of the biggest breakthroughs came when astronomers discovered a quasar from just 670 million years after the Big Bang. That might sound like a long time, but in cosmic terms, it's nothing. This means that supermassive black holes were already in place when the universe was still young. And that means we're missing something big in our understanding of how they formed. The search continues. Every time a new telescope is launched, we get a little closer to answering the mystery of the first quasars. But for now, they remain one of the greatest unsolved puzzles in astronomy. How did they form so quickly? What role did they play in shaping the universe? And could studying them help us understand the nature of black holes themselves? One thing is certain: quasars are more than just cosmic lighthouses. They are windows into the past, showing us a universe that was far more dynamic and chaotic than we ever imagined. And as technology improves, we may finally uncover the secrets of these ancient objects. But until then, the mystery remains, waiting for the next discovery to change everything we thought we knew. The deeper we look into space, the closer we get to answering one of the biggest questions in astronomy: how did the first quasars form? But every discovery seems to bring more questions than answers. Scientists expected to find young, growing black holes in the early universe, small objects still in the process of accumulating mass. Instead, they found fully formed supermassive black holes, billions of times the mass of the Sun, shining as quasars just a few 100 million years after the Big Bang. That shouldn't be possible. This paradox has led to some of the most intense debates in modern astrophysics. Did black holes form differently in the early universe? Were conditions somehow different back then? Or is there an entirely new process at play that we haven't even considered yet? To solve this, we have to dive even deeper into what we know about black holes, quasars, and the structure of the universe itself. One of the key factors in this mystery is the process of black hole growth. Normally, black holes form from the collapse of massive stars. These stellar black holes then grow over time by pulling in gas and merging with other black holes. But this process is slow. Even under ideal conditions, it should take billions of years for a black hole to reach the size of the ones we see in early quasars. So how did these black holes reach their massive sizes in just a few 100 million years? Astronomers have proposed several theories. One of the most intriguing is the idea that some black holes didn't start as collapsed stars at all. Instead, they may have formed directly from enormous clouds of gas collapsing under their own gravity. These direct collapsed black holes would have skipped the entire star-forming phase, going straight from a dense gas cloud to a massive black hole in one step. If this happened, it would explain how some black holes could have started out much larger than expected, giving them a head start in becoming quasars. But even if these early black holes started out bigger, they still had to grow incredibly fast to reach the sizes we see. That brings us to another mystery: the feeding process. Black holes grow by pulling in matter, but there's a limit to how fast they can do this. As gas falls into a black hole, it heats up and produces radiation. This radiation pushes outward, creating a balance known as the Eddington limit. If a black hole tries to pull in matter faster than this limit allows, the radiation pressure pushes material away, slowing its growth. But what if the first black holes found a way around this limit? Some scientists believe that in the early universe, black holes might have been buried inside thick clouds of gas that allowed them to feed much faster than usual. These clouds could have blocked some of the radiation from escaping, preventing it from pushing material away. If that's the case, early black holes could have grown at a rate far beyond what we see in the modern universe. Another possibility is that the first quasars formed in regions of space where conditions were just right for extreme black hole growth. In some parts of the early universe, gas might have been denser and more concentrated, creating ideal feeding grounds for black holes. If these regions existed, then some black holes could have grown much faster than others, explaining why we see some quasars forming so early. But there's still one more mystery. How did these early black holes affect the universe around them? Quasars are incredibly powerful. As they consume matter, they release huge amounts of energy, creating powerful jets of radiation that can reshape entire galaxies. In fact, some scientists believe that quasars played a major role in the evolution of the universe itself. During the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen gas. This gas absorbed light, making the early universe a dark and opaque place. But at some point, something happened that changed everything: the process of cosmic reionization. This was the moment when the first sources of light, including quasars, began to ionize the surrounding gas, making the universe transparent for the first time. Many scientists believe that early quasars played a key role in this transformation. Their intense radiation would have blasted away neutral hydrogen, clearing out space and allowing light to travel freely. But this raises another question. If quasars were responsible for reionization, why do we see so few of them? There should have been thousands of these objects lighting up the early universe, yet we've only found a handful so far. This suggests that either quasars weren't the main drivers of reionization, or we're still missing a large population of them. The search for the first quasars continues, and with each new discovery, we get closer to understanding their origins. The James Webb Space Telescope has already found some of the most distant quasars ever seen, pushing the boundaries of our knowledge even further. But there are still so many unanswered questions. How did these objects form so quickly? What role did they play in shaping the early universe? And could studying them help us unlock the secrets of black hole physics? One of the most exciting possibilities is that the first quasars could hold clues about an entirely new type of physics. Some scientists believe that if we study these objects closely enough, we might find evidence of unknown forces or even hints about the nature of dark matter. After all, if the early universe was somehow different from what we expect, then studying its most extreme objects, like quasars, could reveal things we never imagined. For now, the mystery remains unsolved. But one thing is certain: the first quasars are more than just distant points of light. They are cosmic time capsules, windows into an era of the universe that we are only beginning to understand. And as our technology improves, we may finally get the answers we've been searching for. Until then, the hunt continues, and with each new discovery, we move one step closer to unlocking one of the greatest secrets of the cosmos. The challenge of understanding the first quasars is deeply tied to the limits of our observational technology. While telescopes like Hubble provided some of the first glimpses of ancient quasars, their light is so redshifted, stretched by the expansion of the universe, that only instruments capable of detecting infrared wavelengths can truly study them. This is where the James Webb Space Telescope, JWST, comes in. Unlike its predecessors, JWST is designed specifically to peer into the early universe, capturing light that has traveled for more than 13 billion years. One of JWST's primary missions is to detect and analyze the most ancient quasars, pushing our knowledge to the brink of the cosmic dawn. Already, it has identified objects that challenge our existing theories. Some of these early quasars appear even brighter and more powerful than expected, hinting that the processes driving their growth might be even more extreme than previously thought. If these quasars are indeed powered by supermassive black holes, their existence suggests that either black holes formed much earlier than we assumed, or they somehow grew at speeds beyond our known limits. This raises another key question: did early quasars form differently than the ones we see today? In the modern universe, quasars are relatively rare, found at the centers of massive galaxies. They are powered by black holes that have spent billions of years growing and accumulating mass. But in the early universe, conditions were completely different. The first galaxies were chaotic, gas-rich environments with much more material available for black holes to consume. This could mean that the feeding mechanisms of the first quasars were fundamentally different from what we see now. One possibility is that early quasars were fueled by massive streams of cold gas flowing directly into their black holes. In today's universe, most of the gas near black holes is hot, making it harder to fall in. But in the early universe, cold gas streams could have continuously fed black holes at extreme rates, bypassing the usual growth limitations. If this is true, then the first quasars might not just be rare anomalies. They could be evidence of an entire era where black hole formation worked in a completely different way. The presence of early quasars also has major implications for our understanding of galaxy formation. Every massive galaxy we see today harbors a supermassive black hole at its center. But which came first, the galaxy or the black hole? Did black holes form first and then attract gas and stars around them, shaping galaxies from the inside out? Or did galaxies form first, creating environments where black holes could grow? The existence of quasars so early in the universe suggests that black holes might have played a much larger role in galactic evolution than we previously thought. This could mean that some of the first galaxies were shaped not by the gradual accumulation of stars, but by the violent energy released by growing black holes. The radiation from quasars is so intense that it can heat up surrounding gas, preventing new stars from forming. This process, known as quasar feedback, could have dramatically influenced the early universe, shutting down star formation in some regions while triggering it in others. If early quasars were common, they might have been one of the main forces shaping the first galaxies. But if that's the case, why don't we see more evidence of them? One possibility is that early quasars were much more common than we think, but many of them are simply hidden from view. If a quasar is surrounded by thick clouds of dust and gas, its light could be blocked from reaching us. This means that there could be an entire population of early quasars that we've yet to discover. Another possibility is that some early quasars flickered on and off over time. Unlike modern quasars, which can remain active for millions or even billions of years, early quasars might have been much more unstable. They could have rapidly consumed all the available gas in their environment, then gone dormant until new fuel became available. If this is true, then we might only be catching glimpses of early quasars in their brightest moments, missing many that have temporarily turned off. There's also the question of how these early quasars relate to another cosmic mystery, dark matter. Scientists know that dark matter played a crucial role in the formation of the first galaxies, providing the gravitational scaffolding that allowed normal matter to clump together. But could dark matter have also influenced the growth of early black holes? Some researchers believe that dense pockets of dark matter might have helped funnel gas into black holes, accelerating their growth. Others have even suggested that the first black holes might have formed directly from dark matter itself, bypassing the need for normal matter entirely. If this idea is correct, then studying early quasars could give us direct clues about the nature of dark matter, one of the biggest unanswered questions in physics. By looking at how these objects formed and evolved, we might find new evidence for the role dark matter played in shaping the universe. But the search for the first quasars is far from over. Even with the power of JWST, we are still only scratching the surface of what lies beyond our current observational limits. As technology advances, future telescopes will push even further, revealing more about these ancient objects and the strange conditions of the early universe. What we do know is that the discovery of these quasars has already changed our understanding of cosmic history. They are living proof that the universe's first billion years were far more complex and dynamic than we ever imagined. Their existence challenges our models of black hole formation, galaxy evolution, and even fundamental physics. And as we continue to uncover more of these ancient beacons, they may hold the key to solving some of the greatest mysteries of the cosmos. The journey to understanding the first quasars is just beginning. But one thing is certain: the more we learn, the more incredible and mysterious the universe becomes. And somewhere out there, beyond the edge of what we can currently see, the answers to these questions are waiting. The search for the first quasars is more than just an exploration of distant objects, it's a journey into the fundamental forces that shaped our universe. The existence of these ancient beacons tells us that supermassive black holes were already present just a few 100 million years after the Big Bang. But this raises another mystery. How did they form so quickly? The traditional model of black hole growth struggles to explain how such massive objects could exist in the early universe. Normally, black holes form from the collapse of massive stars. Over time, they grow by pulling in gas, dust, and even merging with other black holes. But this process takes time, far more than the age of the universe when these quasars were already shining. If the first quasars were powered by black holes millions or even billions of times the mass of the Sun, they must have grown at an incredibly fast rate. This is known as the black hole seed problem. How did these objects start, and what allowed them to reach such immense sizes so quickly? One possibility is that the first black holes formed in an entirely different way than the ones we see today. Instead of being born from dying stars, some scientists believe they could have emerged directly from collapsing clouds of gas. These direct collapsed black holes could have formed with masses thousands of times greater than a normal stellar mass black hole, giving them a head start in their growth. If this is true, then the first quasars might be evidence of a completely different pathway for black hole formation, one that no longer exists in the modern universe. But even if these early black holes had a head start, there's still the question of how they managed to grow so quickly. Black holes don't just pull in matter endlessly. There's a limit to how fast they can grow, known as the Eddington limit. When gas falls into a black hole, it heats up and produces intense radiation, creating pressure that pushes against incoming material. If a black hole grows too fast, this pressure should stop more gas from falling in, effectively capping its growth rate. But the first quasars seem to have defied this limit, suggesting that they were growing in ways we don't fully understand. Some scientists propose that these early black holes were fed in massive bursts, with entire galaxies funneling gas directly into them. Others suggest that black holes in the early universe were growing through super-Eddington accretion, a process where gas flows in so rapidly that it overwhelms the usual limits. If true, this would mean that the physics governing black hole growth in the early universe was fundamentally different from what we see today. Another mystery surrounding the first quasars is their connection to dark matter. We know that galaxies and black holes form in regions where dark matter is densest, creating gravitational wells that pull in normal matter. But what if dark matter itself played a more direct role in the formation of the first black holes? Some theories suggest that dense clumps of dark matter could have triggered the collapse of gas clouds, speeding up the birth of supermassive black holes. Others even propose that some of the first black holes might have been made entirely of dark matter, rather than normal baryonic matter. If this idea is correct, then studying early quasars could provide one of the first real clues about the nature of dark matter. By analyzing their distribution and growth, we might be able to determine whether dark matter played an active role in their formation, or if it was simply a passive ingredient in the cosmic recipe. The existence of these ancient quasars also raises profound questions about the structure of the early universe. The light from quasars acts like a cosmic time machine, allowing us to see how the universe evolved over time. By studying the spectra of quasars, astronomers can analyze the gas that surrounded them billions of years ago. This has led to the discovery that the early universe underwent a major transformation known as reionization. Reionization was the period when the first stars and quasars flooded the universe with high-energy radiation, stripping electrons from hydrogen atoms and making the universe transparent to light. Before this era, the universe was filled with a dense fog of neutral hydrogen, blocking most visible light from traveling freely. The presence of bright quasars in this era suggests that they played a key role in clearing away this cosmic fog, reshaping the universe into the transparent state we see today. But this creates another puzzle. Were quasars the main drivers of reionization, or were they just part of the process? Some scientists argue that the first galaxies, with their massive bursts of star formation, were responsible for most of the ionization. Others believe that quasars, with their powerful radiation, were the real culprits. If early quasars were much more common than we think, they could have been the primary force behind this transformation. However, if quasars were so influential in the early universe, why do we see so few of them today? One reason might be that many of the first quasars burned out quickly, exhausting their fuel supplies and leaving behind only dormant black holes. Another possibility is that our current telescopes simply aren't sensitive enough to detect them all. If many early quasars were hidden behind thick clouds of gas and dust, their light would be obscured, making them invisible to traditional telescopes. This is where the next generation of telescopes, like the upcoming Extremely Large Telescope, ELT, will play a crucial role. With its massive mirror and advanced instruments, ELT will be able to peer deeper into the universe than ever before, potentially uncovering a hidden population of early quasars. If these objects are more common than we currently think, they could provide the missing link in our understanding of cosmic evolution. The search for the first quasars is more than just an academic pursuit, it's a quest to answer some of the biggest questions in astrophysics. How did the first black holes form? What role did they play in shaping galaxies? And could they hold clues to the nature of dark matter? Every new discovery pushes the boundaries of our knowledge, revealing a universe that is far more complex and mysterious than we ever imagined. What's truly remarkable is that, despite all our advancements, we are still just scratching the surface. The first quasars represent only the beginning of the cosmic story, a glimpse into an era that remains largely unexplored. As new telescopes come online and our understanding deepens, we may find that the universe's earliest days were even stranger and more fascinating than we ever thought possible. For now, the search continues. And with every new quasar we discover, we take one step closer to unraveling the secrets of the universe's first billion years. The answers are out there, waiting for us to find them. The search for the first quasars is more than just a scientific endeavor, it's a race against time. The further we look into the universe, the deeper we reach into the past, but there's a limit to how far light can travel before it becomes impossible to detect. This is known as the cosmic horizon, the point beyond which light from the earliest quasars has been stretched so much by the expansion of the universe that it no longer falls within the range of our telescopes. However, even within this cosmic limit, the discovery of new quasars from the early universe keeps challenging our understanding of how black holes and galaxies formed. One of the most exciting aspects of this research is that the more we search, the more unusual and extreme cases we find. Some quasars appear to be consuming matter at rates far beyond what should be possible, while others seem to exist in environments that shouldn't have been able to support such massive black holes so early in cosmic history. One of the biggest breakthroughs in recent years has been the discovery of quasars that existed less than a billion years after the Big Bang. These objects are incredibly bright, powered by black holes that are hundreds of millions, sometimes even billions, of times the mass of the Sun. Their presence suggests that supermassive black holes must have formed and grown at an astonishing rate, far faster than conventional theories of black hole growth allow. To explain this rapid formation, scientists have proposed several possible scenarios. One idea is that the first black holes were born not from dying stars, but from direct collapses of enormous gas clouds. This would allow them to start with much larger masses than typical black holes today, bypassing the slow early stages of growth. Another possibility is that these black holes experienced periods of hyperfast feeding, where massive amounts of gas fell into them in short bursts, temporarily overcoming the usual growth limits imposed by radiation pressure. But even if we assume that early black holes grew at extreme rates, another mystery remains. Why do we see quasars in some regions of the universe and not others? The distribution of these objects suggests that they formed in special environments, perhaps in regions where dark matter was unusually dense, or where early galaxy collisions funneled enormous amounts of gas into central black holes. This raises deeper questions about the role of dark matter in the formation of early galaxies and whether the presence of supermassive black holes influenced their evolution in ways we don't yet understand. Quasars also serve as cosmic lighthouses, illuminating the conditions of the universe at different points in time. By analyzing the light from quasars, astronomers can study the composition of the intergalactic medium, the vast space between galaxies filled with gas and dust. This has led to discoveries about the Reionization era, a period when the first galaxies and quasars transformed the universe by ionizing the hydrogen gas that once filled all of space. One of the most significant findings in recent years is that the first quasars may have played a major role in reionization, clearing away the cosmic fog that once made the universe opaque. The intense radiation from these objects would have been powerful enough to strip electrons from hydrogen atoms, turning the neutral gas into ionized plasma. But exactly how much quasars contributed to this process compared to early stars remains a subject of debate. Some models suggest that quasars were the dominant force behind reionization, while others argue that galaxies filled with young, hot stars did most of the work. Regardless of their role in reionization, quasars provide an invaluable tool for studying the history of the universe. Their light carries signatures of the elements present in the early universe, allowing astronomers to track the buildup of heavier elements over time. This is crucial for understanding how the first generations of stars enriched the cosmos with elements like carbon, oxygen, and iron, ingredients necessary for the formation of planets and life as we know it. Another surprising discovery is that some of the earliest quasars appear to be surrounded by massive reservoirs of cold gas, much more than expected. This suggests that the early universe may have been much more efficient at fueling black holes than we thought. If true, it could explain why supermassive black holes were able to grow so quickly, reaching enormous sizes in a relatively short period of time. As telescopes continue to improve, we are likely to find even earlier quasars, pushing the limits of our understanding even further. The upcoming James Webb Space Telescope, for example, has the potential to detect quasars from even closer to the Big Bang, possibly revealing the very first generation of these objects. Other projects, like the Extremely Large Telescope, ELT, will allow astronomers to study early quasars in unprecedented detail, analyzing their structures, growth patterns, and environments. One of the most exciting possibilities is that future observations could reveal entirely new types of quasars, ones that don't fit into our current models at all. Some scientists speculate that the first quasars might have been much dimmer than the ones we see today, powered by smaller black holes that have since faded into obscurity. Others suggest that we might find evidence of failed quasars, black holes that started growing but ran out of fuel before they could become fully active. The search for the first quasars is far from over. Every new discovery raises new questions, forcing us to rethink our assumptions about the early universe. What we learn from these distant beacons will not only help us understand the origins of black holes and galaxies, but may also provide clues about the nature of dark matter, the physics of extreme environments, and the ultimate fate of the universe itself. For now, we continue to look deeper into space, searching for the next breakthrough. The answers are out there, hidden in the light of the most ancient quasars, waiting to be uncovered. The search for the first quasars isn't just about looking back in time. It's about rewriting the history of the universe itself. Every time we push the boundaries of what we can observe, we uncover new details that challenge our understanding of how black holes, galaxies, and cosmic structures formed. The deeper we look, the stranger things become, revealing a universe that seems to have evolved far more quickly than we ever imagined. One of the most baffling aspects of early quasars is their sheer size. These objects, powered by supermassive black holes billions of times the mass of the Sun, existed when the universe was only a few 100 million years old. That shouldn't be possible, not according to our current models of how black holes grow. If black holes formed from the collapse of massive stars, they should have started out relatively small, growing slowly over billions of years as they consumed surrounding gas and merged with other black holes. Yet, here we are, observing quasars that defy these expectations. Scientists have proposed several explanations, but each one comes with its own set of problems. One idea is that the first black holes didn't form from dying stars but instead emerged directly from enormous collapsing gas clouds. This would allow them to start with much larger masses, skipping the slow growth phase that traditional black holes undergo. But this theory raises another question. What conditions would allow such massive clouds to collapse directly into black holes without first forming stars? Another possibility is that early black holes experienced extreme feeding frenzies, devouring enormous amounts of gas at rates far beyond what we see today. Normally, when a black hole consumes matter too quickly, the intense radiation it emits creates pressure that pushes the surrounding gas away, limiting further growth. But if early quasars somehow bypassed this limit, perhaps because they were surrounded by unusually dense and cold gas, their black holes could have grown much faster than expected. Some researchers suggest that early quasars might have formed in rare regions of the universe where conditions were just right for rapid growth. These regions could have contained exceptionally high concentrations of dark matter, the mysterious substance that makes up most of the universe's mass but remains invisible to our instruments. If dark matter played a role in funneling gas into these early black holes, it could explain their rapid growth. However, since we still don't fully understand what dark matter is or how it interacts with normal matter, this idea remains speculative. Beyond the mystery of how these quasars formed, there's also the question of what impact they had on their surroundings. The intense radiation from a quasar is capable of heating and ionizing vast regions of space, potentially shutting down star formation in nearby galaxies. This means that early quasars might not have just been passive objects growing in isolation. They could have actively shaped the evolution of the universe itself. Observations of early quasars also provide valuable clues about the chemical composition of the universe during its first billion years. By analyzing the light from these objects, astronomers can determine what elements were present in the gas that surrounded them. This has revealed that even the earliest quasars contained heavy elements like carbon, oxygen, and iron, elements that could only have been produced by earlier generations of stars. This suggests that star formation and supernova explosions must have been occurring at a rapid pace, enriching the universe with heavy elements much faster than previously thought. Some quasars appear to be surrounded by enormous reservoirs of cold gas, far more than expected. This suggests that the early universe was an extremely efficient environment for fueling black holes. But where did all this gas come from? One possibility is that early galaxies were far more gas-rich than their modern counterparts, providing a steady supply of material for black holes to consume. Another idea is that galaxy mergers played a crucial role, with collisions between young galaxies driving vast amounts of gas into the central black holes. Interestingly, some early quasars appear to be located in massive, dense clusters of galaxies, while others exist in relative isolation. This raises the question of whether the environment played a key role in quasar formation. If quasars needed specific conditions to grow rapidly, understanding their distribution could help us unlock the secrets of how they emerged. The discovery of early quasars has also forced astronomers to rethink their models of galaxy formation. Traditionally, we thought that galaxies formed first, slowly building up their mass before developing supermassive black holes at their centers. But the existence of massive quasars in the early universe suggests that black holes may have formed first, with galaxies assembling around them later. If this is true, it could mean that black holes played a much more active role in shaping the universe than we previously thought. Future telescopes will play a crucial role in answering these questions. The James Webb Space Telescope, JWST, has already begun identifying some of the oldest quasars ever discovered, and upcoming observatories like the Extremely Large Telescope, ELT, will allow scientists to study them in unprecedented detail. These instruments will help determine the exact masses of early quasars, measure the composition of the gas surrounding them, and reveal how they influence their environments. There's also the possibility that we haven't even seen the first quasars yet. Current technology limits how far we can look, but as new telescopes come online, we may find even earlier quasars, ones that existed when the universe was less than 500 million years old. If that happens, it will push the limits of our understanding even further, forcing us to reconsider how the first structures in the universe formed. Another fascinating possibility is that some of the first quasars may no longer be visible because they've gone dormant. Not all quasars remain active forever. Some eventually run out of fuel and fade away, leaving behind massive but inactive black holes. If this happened to some of the first quasars, it could mean that there are relics of these ancient objects hiding in the modern universe, waiting to be discovered. The search for the first quasars is far from over. With every new discovery, we uncover new mysteries, forcing us to rethink our assumptions about the early universe. What we learn from these distant beacons won't just tell us about quasars themselves, it will provide crucial insights into the nature of black holes, the evolution of galaxies, and the fundamental forces that shape the cosmos. For now, all we can do is keep looking, keep questioning, and keep pushing the boundaries of what we know. The answers are out there, hidden in the light of the universe's first quasars, waiting to be uncovered. The search for the first quasars is more than just an exploration of distant objects, it's a direct window into the infancy of the cosmos. Every time we refine our instruments and push our observational limits, we get closer to answering some of the most fundamental questions about the universe. How did the first black holes form? What role did they play in shaping galaxies? And perhaps most intriguingly, are there quasars even older than the ones we found? One of the biggest surprises in this search has been just how early these massive quasars appeared. Some of the most distant quasars discovered are seen as they were when the universe was only 600 million years old. That might sound like a long time, but in cosmic terms, it's a blink of an eye, less than 5% of the universe's current age. The problem is, according to standard models of black hole growth, there shouldn't have been enough time for black holes to reach the billions of solar masses we observe in these quasars. This is why finding even earlier quasars would be so groundbreaking. If we can detect quasars from an even younger cosmic age, it could completely reshape our understanding of black hole formation. One of the key challenges in finding these objects is that they are incredibly far away, meaning their light is stretched by the expansion of the universe, a phenomenon known as redshift. The higher the redshift, the further back in time we're looking. Some of the earliest quasars discovered so far have redshifts greater than 7, meaning their light has been traveling for over 13 billion years to reach us. Finding quasars at even higher redshifts, closer to 10 or beyond, would push the limits of what we currently believe is possible. To find these first quasars, astronomers rely on a variety of techniques. One of the most effective is looking for their distinctive ultraviolet light signatures, which get shifted into the infrared due to cosmic expansion. This is where telescopes like the James Webb Space Telescope, JWST, become invaluable. Unlike previous telescopes, JWST is specifically designed to observe in the infrared, making it uniquely suited for detecting the faint, redshifted light of the first quasars. But even when we find these ancient quasars, the mysteries don't end there. Another big question is what kind of environments they existed in. We know that quasars are powered by supermassive black holes, but those black holes had to form within galaxies. So what did the first galaxies look like? Were they large, well-formed structures, or were they chaotic, still assembling themselves from smaller fragments? Recent observations suggest that early quasars may have been surrounded by dense, turbulent regions of space, filled with vast amounts of gas and dust. This could explain how they were able to grow so quickly. If they were located in areas rich in fuel, they could have fed at extreme rates, reaching massive sizes in record time. But this raises another question. If some black holes could grow so fast, why didn't all of them? Why do we see some quasars as giants while others seem to have stayed small? One possibility is that the first quasars formed in rare, special environments where conditions were just right for extreme growth. Perhaps certain regions of the early universe had much higher densities of gas, allowing black holes there to feed at much higher rates. If so, that would mean that the first quasars aren't evenly spread throughout the universe but are instead clustered in specific locations. There's also the question of how these early quasars interacted with their surroundings. The intense radiation from a quasar is capable of ionizing huge regions of space, stripping electrons from atoms and fundamentally changing the nature of the intergalactic medium. This process, known as cosmic reionization, is one of the most important events in the history of the universe. But did quasars play a major role in this event, or were other sources, such as early galaxies and massive stars, more responsible? To answer this, astronomers look at the light from early quasars to see how much of the surrounding hydrogen is still neutral. If a quasar is found in a region where the hydrogen is mostly ionized, that suggests quasars were a driving force in reionization. If not, it means something else must have done most of the work. Recent studies suggest that while quasars may have contributed to reionization, they probably weren't the main cause. Instead, it seems likely that the combined light from millions of early stars played the biggest role. But quasars still provide crucial clues about this era, helping us understand how the universe transitioned from the Dark Ages, when no light could escape, to the transparent cosmos we see today. Another aspect of the first quasars that remains a mystery is their connection to dark matter. We know that galaxies, including those hosting quasars, form within halos of dark matter, the invisible substance that makes up most of the universe's mass. But how did dark matter influence the growth of these early black holes? Did denser dark matter halos create ideal environments for rapid black hole growth? And could dark matter itself play a more direct role in fueling quasars? Some theories suggest that if dark matter interacts with itself in ways we don't yet understand, it could help funnel normal matter into black holes, accelerating their growth. If true, that would mean that studying the first quasars isn't just about understanding black holes. It could also help us unlock the secrets of dark matter itself. One of the most exciting developments in this field is the possibility of finding quasars that existed even earlier than those we've already detected. Some researchers believe that with the right technology, we could discover quasars from when the universe was just 400 million years old, or even younger. If that happens, it would force us to rethink everything we thought we knew about how black holes formed and evolved. Future telescopes, such as the Extremely Large Telescope, ELT, and the Square Kilometre Array, SK, will allow astronomers to study these distant quasars in unprecedented detail. By analyzing their spectra, we can learn not just about the black holes powering them, but also about the galaxies they inhabit, the gas that surrounds them, and the larger cosmic structures they are part of. The search for the first quasars is ultimately a search for the universe's origins. By looking at these ancient beacons, we're not just seeing distant objects, we're witnessing the story of how everything we see today came to be. And as we continue to push the limits of our observations, we may find that the first quasars hold even more secrets than we ever imagined. The search for the first quasars is like an archaeological dig into the deepest layers of time. Every new discovery adds another piece to the puzzle of how the universe evolved, but it also raises new questions. One of the biggest mysteries still unsolved is how these supermassive black holes formed so quickly. Black holes grow by consuming gas, dust, and sometimes even entire stars, but there is a limit to how fast they can grow. If they feed too aggressively, the radiation they produce pushes material away, slowing down their growth. This self-regulating process is why scientists struggle to explain how some quasars reached billions of solar masses so soon after the Big Bang. One possible explanation is that the first black holes didn't form from dying stars like the ones we see today. Instead, they might have come from something called direct collapse black holes. These would have formed when massive clouds of gas collapsed directly into black holes, skipping the star phase entirely. If this happened, it would explain how some quasars became so large in such a short time. But direct collapse black holes aren't the only theory. Another idea suggests that the first black holes may have started small but merged rapidly with others. In the chaotic early universe, galaxies were much closer together, meaning black holes could have collided and merged far more often than they do today. If this happened frequently enough, it could explain how some black holes reached enormous sizes much earlier than expected. The challenge with these theories is that we don't yet have direct evidence for them. We can't see the very first moments of black hole formation, so we have to rely on indirect clues. One way astronomers try to test these ideas is by studying the environments around early quasars. If direct collapse black holes were common, we should see signs of massive, undisturbed gas clouds in the regions surrounding these quasars. If mergers were the main driver, we should see evidence of violent interactions between galaxies in these areas. This is why telescopes like the James Webb Space Telescope, JWST, are so important. With its powerful infrared capabilities, JWST can peer deeper into the universe than ever before, allowing astronomers to study the first quasars in incredible detail. Already, JWST has found galaxies and black holes that challenge existing theories, suggesting that the early universe was far more complex than we previously thought. Another mystery surrounding early quasars is their connection to galaxy formation. Today, we know that most large galaxies, including our own Milky Way, have supermassive black holes at their centers. But we still don't know whether the black holes formed first and then attracted galaxies around them, or if the galaxies formed first and their central black holes grew over time. Studying the first quasars could help answer this question by revealing whether early black holes existed before fully formed galaxies. There's also the question of how these ancient quasars influenced the universe around them. The light from a quasar is so powerful that it can heat up and ionize gas across vast distances. This means that a single quasar can change the properties of its entire cosmic neighborhood, potentially affecting how new stars and galaxies form. By studying these effects, astronomers can learn not just about the quasars themselves, but also about the larger processes that shaped the early universe. One of the most exciting aspects of this research is that we're still just scratching the surface. Every time a new telescope comes online, we push the limits of what we can see. Future observatories like the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, will allow us to study early quasars with even greater precision, potentially revealing details we never imagined. But perhaps the biggest question of all is whether there are quasars even older than the ones we've already found. So far, the most distant quasars we've detected are from when the universe was about 600 million years old. But what if we could find one from 500 million years? Or 400 million? Each new discovery brings us closer to the very first black holes, and with them, the answers to some of the deepest mysteries of the cosmos. If we could find quasars from just 400 million years after the Big Bang, it would completely change our understanding of early black hole formation. Right now, the models struggle to explain how billion solar mass black holes existed at 600 million years. If we push that timeline back even further, it could force scientists to rethink the entire process of black hole growth. One possibility is that our understanding of black hole accretion is incomplete. We assume that black holes grow at a certain rate based on the limits of how much matter they can pull in before radiation pushes material away. But what if early black holes found ways to bypass these limits? Some theories suggest that in the dense environments of the early universe, black holes could have entered a phase of super-Eddington accretion, where they devoured matter much faster than expected. If this happened, it would mean that the first quasars could have grown to enormous sizes in record time. Another radical idea is that some black holes formed from exotic processes beyond normal astrophysics. Some physicists have speculated that primordial black holes might have formed in the first moments after the Big Bang itself. Unlike black holes that come from collapsing stars, these would have originated from density fluctuations in the early universe, collapsing into black holes almost instantly. If even a small fraction of these primordial black holes grew into quasars, it could explain why we see supermassive black holes so early in cosmic history. The hunt for the first quasars is also deeply connected to another mystery, the first galaxies. We know that quasars exist within galaxies, but in the early universe, both were still forming. Were the first galaxies chaotic, swirling masses of gas with a growing black hole in the center? Or did the black holes stabilize and shape their host galaxies from the start? Some observations suggest that early quasars were surrounded by thick clouds of gas and dust, possibly hiding the true structure of their galaxies. If this is the case, it could mean that early galaxies were still in the process of assembling themselves while their central black holes were already active. This would support the idea that black holes might have played a leading role in shaping the first galaxies, rather than being passive components within them. To solve this puzzle, astronomers are using advanced techniques like gravitational lensing, where massive objects in space act as natural magnifying glasses, bending and amplifying the light from distant quasars. This allows us to see details that would otherwise be impossible to detect. Some of the most distant quasars discovered so far have been found using this method, and future surveys will likely uncover even more. But there's another layer to this mystery: dark matter. We know that galaxies form within halos of dark matter, the invisible substance that makes up most of the universe's mass. Could dark matter have played a role in the formation of the first quasars? Some theories suggest that if dark matter has self-interacting properties, meaning it can clump together in unusual ways, it might have helped funnel normal matter into the first black holes, accelerating their growth. If this is true, then studying the earliest quasars could give us clues about dark matter itself, one of the biggest unsolved mysteries in physics. Another pressing question is how early quasars influenced the larger universe. We know that quasars are among the brightest objects in existence, pouring out energy across vast distances. This intense radiation likely played a role in the process of cosmic reionization, the event that transformed the universe from a foggy, opaque state into the transparent cosmos we see today. But how much did quasars contribute to this process compared to the first stars and galaxies? To answer this, astronomers are studying the light from early quasars to see how much neutral hydrogen still existed in their surroundings. If we find a quasar deep in a region of mostly neutral hydrogen, it means reionization was still in progress at that time. If we find one in a fully ionized region, it suggests that reionization happened earlier than expected. These measurements can help us reconstruct the timeline of the universe's transformation and determine the role quasars played in shaping it. The future of this research is incredibly exciting. Upcoming telescopes, such as the Extremely Large Telescope, ELT, and the Square Kilometer Array, SKA, will provide even sharper views of early quasars. ELT, with its massive 39-meter mirror, will allow astronomers to study the detailed composition of quasar host galaxies, while SKA will map the distribution of neutral hydrogen across cosmic history, revealing how quasars influenced their surroundings. One of the most ambitious goals is to find the very first quasar, the one that marks the true beginning of supermassive black hole formation. Whether we find it at a redshift of 10, 15, or beyond, it will be a discovery that reshapes our understanding of the universe's first billion years. Every new quasar we find is a step closer to uncovering the deepest secrets of cosmic history. With each discovery, we refine our models, challenge our assumptions, and push the boundaries of what we know. And as we continue searching, one thing is certain: the first quasars are out there, waiting to reveal the untold story of how the universe's most powerful objects came to be. The search for the first quasars is far from over, and with every new discovery, the mystery deepens. One of the most perplexing aspects of these ancient beacons is how they managed to gather enough matter to shine so brightly in such a short time. Normally, a black hole's growth is limited by a process called the Eddington limit, which prevents it from consuming matter at an unlimited rate. But if these first quasars truly existed less than a billion years after the Big Bang, they must have found a way to break the conventional rules of black hole growth. Some researchers believe that the answer lies in super-Eddington accretion, a process where black holes consume material at rates much higher than previously thought possible. In this scenario, dense clouds of gas would have collapsed onto the black holes so rapidly that the radiation pressure, which normally slows down accretion, couldn't push the material away fast enough. This could have led to an extreme growth phase, allowing these black holes to reach billions of solar masses in record time. However, the problem with this theory is that we haven't seen direct evidence of such rapid growth in modern black holes. If super-Eddington accretion was a common process in the early universe, why don't we see it happening today? One possibility is that conditions in the early universe were dramatically different, with much more gas available for black holes to consume. Another idea is that modern black holes may still experience super-Eddington accretion, but the effects are hidden by thick layers of gas and dust. Another theory that could explain the rapid formation of quasars is the existence of seed black holes that were much larger than the ones we see forming today. Normally, black holes form when massive stars collapse at the end of their lives, creating objects that are a few times the mass of the Sun. But if the first black holes formed differently, perhaps through the direct collapse of massive gas clouds, they could have started out much larger, giving them a head start in their growth. These direct collapse black holes would have skipped the usual star-forming process, allowing them to become massive almost immediately. Some simulations suggest that if conditions were right, these early black holes could have formed with masses of 100,000 to 1 million times that of the Sun. If true, This would explain why we see such massive quasars so early in the universe's history. But even if the first black holes started large, their rapid growth remains a puzzle. One idea that has gained traction is that early galaxies were much more chaotic than the ones we see today. In the present universe, galaxies tend to be relatively stable, with stars, gas, and black holes moving in predictable patterns. But in the early universe, galaxies were colliding and merging at an incredible rate, creating turbulent environments where black holes could rapidly consume surrounding material. If these early galaxies were constantly feeding their central black holes, it could explain why we see quasars shining so brightly at such early times. This chaotic feeding process may have allowed black holes to temporarily bypass the usual growth limits, accelerating their expansion to supermassive scales. The role of dark matter in this process is another major mystery. We know that dark matter plays a crucial role in galaxy formation, providing the gravitational scaffolding that allows normal matter to clump together and form structures. But could dark matter have also played a role in the formation of the first quasars? Some researchers have proposed that dark matter halos might have funneled gas directly into the centers of early galaxies, creating ideal conditions for black hole growth. If this process occurred efficiently, it could explain how some quasars grew to enormous sizes so quickly. Others have suggested that certain types of dark matter interactions could have helped trigger the formation of the first black holes, perhaps by causing small fluctuations in density that led to rapid collapse. To test these ideas, astronomers are looking at the environments around early quasars, searching for clues about how they formed. By studying the distribution of gas, stars, and dark matter near these objects, scientists can piece together the conditions that allowed them to exist. Advanced telescopes like the James Webb Space Telescope, JWST, and upcoming observatories like the Extremely Large Telescope, ELT, are playing a crucial role in this search. One of the most exciting discoveries from JWST so far has been the detection of galaxies that existed alongside the earliest quasars. These galaxies appear to be surprisingly mature, with structures that challenge existing models of how galaxies form. If galaxies were already well developed when the first quasars appeared, it raises new questions about the timeline of cosmic evolution. Did galaxies form first, with their central black holes growing later? Or did black holes form early and shape the galaxies around them? The answer to this question could have profound implications for our understanding of the universe. If quasars played a leading role in galaxy formation, it would suggest that supermassive black holes are not just byproducts of galaxy evolution, but fundamental components of the cosmic order. Another major mystery is how the light from early quasars influenced their surroundings. Quasars are so powerful that they can ionize huge regions of space, stripping electrons from atoms and altering the state of the intergalactic medium. This process, known as reionization, transformed the universe from a dark, neutral gas-filled environment into the transparent cosmos we see today. But exactly how much quasars contributed to reionization remains an open question. Some studies suggest that they played a major role, while others argue that early stars and galaxies were the primary drivers of this transformation. To solve this puzzle, astronomers are studying the light from distant quasars to measure the amount of neutral hydrogen in their surroundings. If quasars were significant contributors to reionization, we should see evidence of this in their spectra. One of the most intriguing possibilities is that the first quasars were even more extreme than the ones we've found so far. Could there be quasars that formed even earlier than 600 million years after the Big Bang? If so, finding them would require pushing our observational capabilities to the absolute limit. Future telescopes like the Square Kilometre Array, SKA, will help us search for these elusive objects by mapping the distribution of neutral hydrogen across the cosmos. By identifying regions where reionization was still occurring, scientists hope to pinpoint the locations of even earlier quasars. If we find one at a redshift of 10 or higher, it would be a groundbreaking discovery, rewriting the history of black hole formation. The search for the first quasars is not just about understanding black holes, it's about understanding the entire history of the universe. These objects are cosmic time capsules, revealing how the universe transitioned from a chaotic, energetic state into the structured cosmos we see today. Every new quasar we discover brings us closer to answering fundamental questions about the nature of black holes, galaxies, and the evolution of the universe itself. But perhaps the most exciting part of this search is the realization that we are still at the beginning. With every new technological advancement, we push the boundaries of what we can see. The earliest quasars are out there, hidden in the depths of space, waiting for us to uncover their secrets. And as we continue this journey, one thing is certain: the story of the first quasars is far from over. Another pressing mystery surrounding the first quasars is the role of cosmic inflation in their formation. Inflation is the rapid expansion of the universe that occurred almost immediately after the Big Bang. This event smoothed out the cosmos while also introducing tiny fluctuations in density, fluctuations that later grew into galaxies, stars, and black holes. But how exactly did these early density variations contribute to the birth of quasars? Did inflation create the conditions necessary for the earliest black holes to form at an accelerated rate? Some researchers believe that inflation may have played a direct role in setting up the extreme conditions needed for supermassive black holes to appear so quickly. If inflation produced certain regions of space that were denser than others, those areas could have collapsed under their own gravity to form massive black hole seeds. This would provide a potential solution to one of the biggest puzzles: how quasars formed so early in the universe's timeline. Another intriguing idea is that primordial black holes, hypothetical black holes that formed directly from density fluctuations in the early universe, could have acted as the first seeds for quasars. Unlike black holes that formed from dying stars, primordial black holes would have been created from the intense gravitational effects of the young universe itself. If any of these objects survived, they could have served as the foundation for the first quasars, growing rapidly by accreting material from their surroundings. This theory is fascinating because it suggests that some of the earliest quasars may not have formed through conventional means at all. Instead of growing from the collapse of massive stars or direct collapse gas clouds, they might have started as primordial black holes, born just fractions of a second after the Big Bang. If this is the case, then studying early quasars could provide evidence for these mysterious objects, and potentially change our understanding of how black holes originate. The nature of the galaxies that hosted the first quasars is another significant mystery. Modern quasars are typically found at the centers of large galaxies, where they feed off the surrounding gas and stars. But what did the galaxies that housed the first quasars look like? Were they chaotic, turbulent places filled with violent star formation and galaxy mergers? Or did they already have some level of order and structure? Observations from the James Webb Space Telescope are beginning to shed light on this question, revealing that the first galaxies were much more massive and complex than previously thought. Some of them appear to have formed large populations of stars in a very short amount of time, challenging existing models of galaxy evolution. If galaxies were already well developed when the first quasars appeared, it could mean that black holes and galaxies evolved together, influencing each other's growth. But there's also the possibility that these early galaxies were incredibly unstable, with gas clouds rapidly collapsing into stars and black holes in a chaotic process. If this was the case, then the environment around the first quasars would have been extremely dynamic, with massive flows of gas feeding into the black hole at breakneck speeds. This could help explain why the first quasars were so luminous. If they were located in highly turbulent regions of space, they may have had access to much more fuel than we initially assumed. Another key piece of the puzzle is the connection between quasars and the cosmic web, the vast, interconnected structure of filaments and voids that make up the large-scale structure of the universe. Quasars don't just appear in random locations. They tend to be found in regions of space where matter is concentrated, such as the intersections of cosmic filaments. This suggests that the first quasars may have been forming in the densest regions of the early universe, where gravity pulled gas into tight clusters. If these quasars were located at the heart of cosmic filaments, they would have had access to massive amounts of material, allowing them to grow rapidly. But this also raises new questions. Why were some of these regions able to form quasars while others did not? Did the first quasars influence the formation of the cosmic web itself? There's also the mystery of quasar winds, powerful outflows of energy and matter that can shape the evolution of entire galaxies. Modern quasars are known to produce incredibly strong winds that can blow away gas from their host galaxies, shutting down star formation and influencing the overall structure of their environment. But did the first quasars also have these powerful outflows? If so, they could have played a major role in shaping the young universe, clearing out gas and regulating the growth of galaxies. Some astronomers suspect that quasar winds were even more extreme in the early universe. If the first quasars were growing at super Eddington rates, then they may have been releasing enormous amounts of radiation and energy, creating massive feedback effects. These outflows could have affected not just their own galaxies but also neighboring galaxies, influencing star formation on a much larger scale. One way to test this idea is by looking for evidence of quasar winds in the spectra of early quasars. If these outflows were strong enough, they should have left distinct signatures in the surrounding gas, altering its composition and temperature. By studying the light that passes through these regions, astronomers can determine whether the first quasars were producing winds powerful enough to shape their environment. But the most profound question of all remains: what happened to the first quasars? Many of the ancient quasars we observe are no longer active, meaning their black holes have stopped consuming large amounts of material. Did they simply run out of fuel? Or did some other process shut them down? One possibility is that the first quasars eventually consumed all the available gas in their surroundings, leaving them with nothing left to feed on. As galaxies evolved and settled into more stable configurations, the chaotic inflows of gas that fueled early quasar growth may have slowed down, causing their brightness to fade. Another possibility is that mergers between galaxies played a role in shutting down quasars. When galaxies collide, their black holes can merge as well, producing gravitational waves and potentially disrupting the accretion process. If two supermassive black holes merged, the resulting black hole might enter a phase where it no longer shines as a quasar, becoming a dormant relic of the early universe. Some researchers also suspect that interactions with dark matter could have played a role in the disappearance of the first quasars. If dark matter influenced the distribution of gas in the early universe, it could have affected how long quasars remained active. Certain models suggest that as dark matter clumps evolved, they may have either fueled or starved quasars, determining their ultimate fate. The search for the first quasars is a journey that is still unfolding. Every new discovery brings fresh questions, pushing the limits of our understanding. But one thing is certain: the existence of these ancient, and possibly bright objects challenges everything we thought we knew about the early universe. What other secrets are hidden in the depths of space, waiting to be uncovered? Could there be even earlier quasars, lurking just beyond the reach of our telescopes? Or are we still missing a key piece of the puzzle that explains how these cosmic beacons came to be? With future telescopes and new technologies, we may finally be on the verge of answering some of these questions. The universe is vast, and its mysteries are endless. But as we continue our search for the first quasars, one thing is clear: the more we learn, the more we realize just how little we truly know. The deeper we look into space, the more we realize that the first quasars may not just be rare cosmic anomalies, but instead key pieces in the puzzle of how the universe evolved. If we can uncover more about their origins, we might gain insight into the conditions that allowed them to exist in the first place. This could change our entire understanding of cosmic history, revealing new mechanisms of black hole growth and galactic formation that we never considered before. One of the most perplexing questions about the first quasars is how they interacted with their surroundings. We know that modern quasars are some of the most influential objects in the universe, shaping entire galaxies through their immense radiation and energy output. But were the first quasars just as powerful, or were they fundamentally different? Some scientists theorize that the first quasars played a role in reionization, the process that made the universe transparent to light. Before this era, the universe was filled with a dense fog of neutral hydrogen that absorbed most radiation. When the first stars and black holes formed, they emitted energy that ionized this hydrogen, clearing the cosmic fog and allowing light to travel freely. If quasars were present during this period, they could have been major contributors to reionization. Their immense energy output would have provided a powerful source of ionizing radiation, accelerating the process, and transforming the universe. However, there's still much debate about whether quasars alone were enough to cause this shift, or if they worked alongside massive populations of early stars. The evidence for quasar involvement in reionization comes from the spectra of distant quasars. When we analyze the light from these ancient objects, we can see how it was affected by the surrounding gas. If a quasar's light passes through a region of neutral hydrogen, it leaves behind a distinctive absorption signature. By studying these signatures, astronomers can determine whether the first quasars were surrounded by ionized bubbles or if they emerged before reionization was complete. So far, observations suggest that the earliest known quasars existed in a partially ionized universe, meaning they may have contributed to reionization but were not the sole cause. This raises even more questions. If quasars weren't the primary drivers of reionization, what else was responsible? And if they did play a role, how exactly did their energy influence the surrounding cosmic gas? One possibility is that quasar-driven winds helped spread ionization across large regions of space. Modern quasars produce incredibly strong outflows of gas, driven by the intense radiation from the black hole's accretion disk. These winds can push gas outward at speeds of thousands of kilometers per second, potentially clearing out surrounding hydrogen and accelerating the ionization process. If the first quasars produced similar winds, they might have created vast ionized bubbles, carving out clearings in the cosmic fog. This could explain why some regions of the early universe became transparent to light faster than others. However, detecting these effects is extremely challenging, as we can only study the distant past through the light that reaches us today. There's also the mystery of how the first quasars managed to sustain their immense energy output. Feeding a supermassive black hole requires an enormous amount of matter, and for a quasar to remain active, it must continuously consume gas from its surroundings. But in the early universe, where gas was more widely distributed, how did quasars maintain such rapid growth? One idea is that quasars formed in environments where gas was being funneled directly into the black hole at high speeds. Galaxy mergers, gravitational interactions, and cosmic filaments could have provided a steady supply of fuel, allowing the quasar to sustain its energy output. If this is the case, then the first quasars may have been located in the busiest regions of the early universe, where matter was being pulled together at an unprecedented rate. Another possibility is that the first quasars underwent episodic feeding cycles. Instead of continuously consuming matter, they may have experienced periods of intense activity followed by quiet phases where little material was available. This could explain why some quasars appear to have grown rapidly before fading away. Perhaps they went through multiple stages of accretion, depending on the availability of nearby gas. There's also the question of what happened to the galaxies that hosted the first quasars. Did they evolve into modern galaxies with dormant supermassive black holes at their centers? Or did they experience such extreme conditions that they were torn apart by gravitational forces? Some researchers believe that the first quasars may have influenced the development of their host galaxies in dramatic ways. If a quasar was powerful enough, it could have heated and expelled vast amounts of gas, shutting down star formation and altering the galaxy's evolution. This is known as quasar feedback, and it's thought to be a key factor in shaping galaxies over time. If the first quasars produced strong feedback effects, they might have caused their host galaxies to evolve differently than those without quasars. Some galaxies may have grown more slowly, while others could have been completely transformed by the energy released from their central black hole. Understanding this process is crucial for unraveling the history of galactic formation in the early universe. Another major mystery is whether all early supermassive black holes became quasars or if some remained hidden. It's possible that many black holes formed in the early universe but never became bright enough to be classified as quasars. These hidden black holes could still exist today, lurking in the centers of ancient galaxies. Finding these hidden black holes is one of the biggest challenges in modern astrophysics. Because they don't emit visible light, they can only be detected through indirect means, such as their gravitational effects on nearby stars or the emission of faint X-rays. If we can locate more of these objects, we might be able to piece together a more complete picture of how supermassive black holes formed and evolved over billions of years. One of the most exciting prospects for the future is the possibility of detecting gravitational waves from the mergers of early supermassive black holes. When two massive black holes collide, they produce ripples in spacetime that can be detected by observatories like LIGO and Virgo. If we can detect gravitational waves from the first quasars, it could provide direct evidence of how these objects formed and interacted in the early universe. Upcoming telescopes and observatories, such as the Laser Interferometer Space Antenna, LISA, will be able to detect these signals with even greater precision. By studying the gravitational waves produced by merging black holes, we may be able to learn more about the environments in which the first quasars formed and how they evolved over time. Another promising avenue of research is the study of relic quasars, ancient quasars that have long since faded but still contain clues about their past. By examining the remnants of these objects, we may be able to determine how they shut down and what factors contributed to their eventual demise. The search for the first quasars is far from over. Every new discovery brings fresh questions and challenges our understanding of the universe's history. Were these objects truly unique, or were they just one part of a much larger cosmic story that we have yet to fully uncover? With each passing year, we get closer to answering these fundamental questions. And as technology advances, we may one day be able to witness the birth of the first quasars in greater detail than ever before. But until then, the mystery remains, waiting for the next great discovery to shine a light on the darkest corners of the cosmos. The search for the first quasars is one of the most ambitious quests in modern astronomy, pushing the limits of what we can observe and understand about the early universe. Every time we find a quasar that existed billions of years ago, we are looking deeper into the past, uncovering snapshots of a time when the universe was still young and chaotic. But even with our most advanced telescopes, there are still so many unknowns, mysteries that keep astronomers searching for more evidence, hoping to fill in the gaps of cosmic history. One of the biggest challenges in studying the first quasars is the immense distance that separates us from them. The light we see from these objects has been traveling for over 13 billion years, meaning that when we observe a quasar today, we are actually looking at it as it appeared in the distant past. But because the universe is expanding, this light is stretched into longer wavelengths, a phenomenon known as redshift. The higher the redshift, the farther away, and the older the quasar is. To detect these extremely distant quasars, astronomers rely on powerful telescopes that can observe light in multiple wavelengths, from visible and ultraviolet to infrared and radio. Instruments like the James Webb Space Telescope, JWST, and the Atacama Large Millimeter/Submillimeter Array, ALMA, are essential for finding quasars that existed when the universe was less than a billion years old. These telescopes allow us to peer through the cosmic dust and gas that often obscure distant objects, revealing details that were previously hidden. But even when we do find a distant quasar, studying it in detail is incredibly difficult. The light from these objects is often faint and scattered, making it challenging to analyze their properties with precision. Scientists have to carefully separate the quasar's light from the surrounding noise, using complex techniques to extract information about its composition, structure, and motion. One of the key questions about the first quasars is how they formed so quickly. In the early universe, conditions were very different from what we see today. The first stars and galaxies were still taking shape, and yet, somehow, supermassive black holes were already present, feeding on matter and producing intense radiation. How did these black holes grow to such enormous sizes in such a short amount of time? One possible explanation is that the first black holes formed directly from massive clouds of gas, rather than from the collapse of stars. In the standard model of black hole formation, a star reaches the end of its life, undergoes a supernova explosion, and collapses into a black hole. But this process takes time, and it's unlikely that stellar mass black holes could have grown into supermassive ones so quickly. Instead, some scientists propose that the first quasars were born from direct collapse black holes, which formed when enormous clouds of gas collapsed under their own gravity without ever forming stars. If this happened in the early universe, it could have created black holes that were already tens of thousands, or even hundreds of thousands of times the mass of the Sun. These massive seeds would then have had a head start, allowing them to rapidly grow into the supermassive black holes we see powering quasars today. Another possibility is that early black holes grew through super-Eddington accretion, a process in which they consumed matter at an exceptionally fast rate. Normally, black holes can only feed at a certain limit, known as the Eddington limit, beyond which the radiation pressure from the infalling material pushes gas away, preventing further growth. But if the first black holes were in extremely dense environments, they might have been able to break this limit, pulling in gas much faster than expected. Recent simulations suggest that this kind of rapid growth could have been possible in the chaotic conditions of the early universe. If early galaxies were merging frequently, they could have funneled vast amounts of gas toward their central black holes, allowing them to grow far more quickly than previously thought. This could explain why we see fully formed supermassive black holes in the first few 100 million years after the Big Bang. But if the first quasars were growing so rapidly, what impact did they have on their surroundings? We know that modern quasars can be incredibly disruptive, blasting out powerful jets of energy and driving massive winds that shape entire galaxies. If the first quasars were just as energetic, they could have played a key role in shaping the structure of the early universe. Some models suggest that quasar-driven winds could have swept through young galaxies, clearing out gas and shutting down star formation. This process, known as quasar feedback, is thought to be one of the reasons why some galaxies stopped forming new stars and became dead, elliptical galaxies. If similar feedback effects were happening in the early universe, they could have influenced the growth of the first galaxies in ways we are only beginning to understand. But there's also another possibility. What if some early quasars were hidden from view? We tend to think of quasars as incredibly bright objects, but not all black holes are actively feeding. Some might have gone through periods of dormancy, where they stopped pulling in large amounts of gas and became much harder to detect. If this happened with the first quasars, it could mean that there are far more early black holes than we currently observe. These silent black holes could still exist today, lurking at the centers of ancient galaxies, waiting to be discovered. Finding them could provide crucial clues about how supermassive black holes evolved over cosmic time. One way to search for hidden black holes is by looking for their gravitational effects on nearby stars. Even if a black hole isn't actively feeding, its immense gravity can still influence the motion of surrounding objects. By studying how stars move in the centers of old galaxies, astronomers can infer the presence of massive black holes that would otherwise remain invisible. Another method involves looking for faint X-ray emissions. Even a dormant black hole can sometimes produce weak bursts of X-rays, which can be detected by space telescopes like Chandra and XMM Newton. If we can find more of these faint signals, we might be able to uncover a whole population of ancient black holes that formed during the era of the first quasars. The more we learn about the first quasars, the more we realize how much we still don't know. Every discovery brings new questions, challenging our understanding of how the universe's most extreme objects came to be. Were the first quasars truly unique, or were they just the brightest members of a much larger population of early black holes? How did they influence their surroundings, and what role did they play in shaping the galaxies we see today? With new telescopes and technology, we are getting closer to answering these questions. The James Webb Space Telescope is already providing unprecedented views of the early universe, revealing objects that were previously invisible to us. Future observatories like the Extremely Large Telescope, ELT, and the Square Kilometer Array, SK, will push the boundaries even further, allowing us to study the first quasars in greater detail than ever before. But for now, the mystery remains. The first quasars are like cosmic ghosts from a time long past, their light carrying secrets from an era we can only glimpse through the lens of our most powerful telescopes. As we continue this search, one thing is certain: the more we uncover, the more we realize just how much of the universe's story is still waiting to be told. The search for the first quasars is not just about looking for the most distant black holes. It's also about piecing together the early history of the universe itself. These quasars serve as cosmic lighthouses, illuminating the environment of the young cosmos. But what was that environment really like? To understand it, we have to go back to a time before quasars even existed, to an era known as the Cosmic Dark Ages. After the Big Bang, the universe was a hot, dense soup of particles. As it expanded, it cooled, and within a few 100,000 years, protons and electrons combined to form neutral hydrogen atoms. This event, known as recombination, allowed light to travel freely for the first time, creating what we now see as the cosmic microwave background radiation. But after this, the universe entered a long period of darkness. There were no stars, no galaxies, and certainly no quasars, just vast clouds of cold hydrogen gas stretching across space. This dark era lasted for hundreds of millions of years until the first stars and galaxies began to form. These early objects emitted intense radiation that started to ionize the surrounding hydrogen, gradually transforming the universe into the transparent, structured cosmos we see today. This process, known as cosmic reionization, is one of the biggest missing pieces in our understanding of the early universe. And this is where quasars become crucial. Because they are so incredibly bright, quasars are among the best tools we have for studying cosmic reionization. As their light travels through the universe, it passes through the intergalactic medium, the vast stretches of space between galaxies. If this medium is neutral, it absorbs certain wavelengths of light, leaving behind characteristic gaps in the quasar's spectrum. By studying these absorption patterns, astronomers can map out when and where reionization occurred, helping us understand how the first galaxies and black holes shaped the cosmos. One of the most important discoveries in this area came from studying a quasar known as ULA's J1120+0641. This quasar, discovered in 2011, is one of the most distant ever found, with a redshift of 7.1, meaning it existed just 770 million years after the Big Bang. When scientists analyzed its light, they found that the space around it was still partially neutral, indicating that reionization was not yet complete. This was one of the first direct pieces of evidence that quasars were forming right in the middle of this cosmic transition. But ULA's J1120+0641 raised even bigger questions. Its central black hole had a mass of around 2 billion times the Sun, yet it existed at a time when the universe was still less than a billion years old. How could such a massive black hole have formed so quickly? This discovery forced astronomers to rethink their models of black hole growth, suggesting that the first quasars may have grown through mechanisms we still don't fully understand. The search for more early quasars continues, with astronomers scouring the sky using telescopes like the Sloan Digital Sky Survey (SDSS) and the Dark Energy Survey (DES). These surveys scan huge portions of the sky, looking for the telltale signs of distant quasars hidden among the countless stars and galaxies. But identifying them is no easy task. Because quasars are so distant, their light is incredibly faint by the time it reaches us. They also have to be distinguished from other objects that can look similar, such as brown dwarfs, failed stars that can mimic the colors of quasars in certain wavelengths. To separate the real quasars from these imposters, astronomers use sophisticated machine learning algorithms that analyze vast amounts of data, picking out the most promising candidates for further study. Once a candidate is identified, follow-up observations are needed to confirm its true nature. This often involves using large ground-based telescopes like the Keck Observatory or the Very Large Telescope, VLT, to take detailed spectra, breaking down the light into its component wavelengths to reveal the signatures of a quasar. Only then can astronomers be sure they have found another piece of the cosmic puzzle. But even as we find more early quasars, one of the biggest mysteries remains. Are we seeing the full picture? Could there be an entire population of quasars we have yet to discover, ones that are hidden from view? Some scientists believe that a significant number of early quasars could be obscured by thick clouds of dust and gas, making them much harder to detect with traditional optical and infrared telescopes. To find these hidden quasars, astronomers are turning to other wavelengths, such as X-rays and radio waves. The Chandra X-ray Observatory and the upcoming Athena mission are designed to detect the high-energy radiation emitted by quasars, even if they are buried in dust. Meanwhile, radio telescopes like the Square Kilometre Array (SKA) will be able to pick up the faint radio signals from these distant objects, helping us build a more complete picture of the quasar population in the early universe. If we do find a large number of hidden quasars, it could change our understanding of how black holes influence the evolution of galaxies. It would suggest that black hole activity in the early universe was even more widespread than we thought, potentially playing an even greater role in shaping the first cosmic structures. At the same time, there's also the possibility that we're missing an even deeper mystery, one that challenges our very models of cosmology. What if the first black holes didn't form in the way we expect? What if they weren't just the result of collapsing gas clouds or merging stars, but something even stranger? Some researchers have proposed that the first black holes could have been primordial in origin, forming directly from density fluctuations in the earliest moments of the Big Bang. If true, this would mean that black holes existed before the first stars and galaxies, acting as seeds for the structures we see today. Finding evidence for primordial black holes would revolutionize our understanding of the early universe, forcing us to rethink everything we know about cosmic history. It could even have implications for the nature of dark matter, since some theories suggest that a fraction of dark matter could be made up of these ancient black holes. The more we search for the first quasars, the more we realize that we are not just studying distant objects, we are unraveling the origins of the universe itself. Every new discovery brings us closer to answering fundamental questions about where we came from and how the cosmos evolved into what we see today. But with every answer, new mysteries arise, ensuring that the search for the first quasars will continue for years to come. As telescopes become more powerful and technology advances, we are on the brink of uncovering secrets that have been hidden for billions of years. The first quasars are out there, waiting to be found. And when we finally piece together their story, we may find that they hold the key to some of the greatest cosmic mysteries of all time. The search for the first quasars is a journey through time, one that forces us to look deeper and question everything we thought we knew about the universe. As we push the limits of our telescopes and refine our techniques, we are constantly uncovering new details that challenge our understanding of black holes, galaxy formation, and the very nature of the cosmos itself. But despite the progress we've made, the deeper we look, the more questions arise. One of the biggest challenges in studying the first quasars is understanding their role in cosmic evolution. These objects aren't just isolated points of light in the sky, they are engines of immense power, capable of shaping entire galaxies. The energy released by a quasar can influence the formation of stars, regulate the growth of galaxies, and even drive outflows of gas that stretch across hundreds of thousands of light years. But how exactly did this feedback process work in the early universe? To answer this question, astronomers use simulations, complex computer models that attempt to recreate the conditions of the young cosmos. By simulating the formation and evolution of quasars, researchers can test different scenarios to see which ones best match the observations. These simulations suggest that quasars played a key role in limiting the growth of massive galaxies. When a supermassive black hole becomes too active, it can release powerful winds that blow away the surrounding gas, preventing further star formation. This process, known as quasar feedback, may be one of the reasons why we don't see as many gigantic galaxies in the present-day universe. But the biggest mystery of all remains: how did the first black holes form in the first place? To create a quasar, you need a supermassive black hole, but forming one so early in the universe's history is not easy. The traditional view is that black holes grow by accreting matter over millions of years, slowly accumulating mass as they pull in surrounding gas and dust. However, this process is not fast enough to explain the existence of quasars like ULA's J1120+0641, which had a mass of 2 billion suns less than a billion years after the Big Bang. This discrepancy has led to several competing theories. One possibility is that the first black holes formed from the collapse of massive clouds of gas, skipping the intermediate star-forming stage entirely. These direct collapse black holes could have formed with masses of tens of thousands of suns, allowing them to grow into quasars much more quickly. Another idea is that the first black holes grew through runaway mergers, small black holes colliding and merging at a rapid rate, building up mass far more quickly than previously thought. A more exotic possibility is that some of the first black holes were primordial, forming in the earliest moments of the universe from fluctuations in the density of space itself. If true, This would mean that black holes have been a fundamental part of the cosmos since the very beginning, possibly even acting as seeds for galaxy formation. To test these theories, astronomers are looking for even earlier quasars, ones that existed even closer to the birth of the universe. The James Webb Space Telescope, JWST, launched in 2021, is one of the most powerful tools we have for this search. With its ability to observe infrared light with incredible precision, JWST can peer deeper into space than any telescope before it, potentially revealing quasars that existed just a few 100 million years after the Big Bang. Already, JWST has made groundbreaking discoveries, detecting galaxies and black holes that challenge existing models of early cosmic evolution. As more data comes in, we may finally get a clearer picture of how the first quasars formed, how they influenced their surroundings, and what role they played in shaping the universe as we know it. But even as we search for these distant beacons, we must also consider the possibility that our understanding of black holes themselves is incomplete. Could there be entirely new physics at play in the extreme environments of the early universe? Some scientists speculate that the first quasars may exhibit behaviors that don't fit within our current models of gravity and quantum mechanics. One of the most intriguing possibilities is the existence of naked singularities, black holes without an event horizon. According to Einstein's general theory of relativity, every black hole should have an event horizon, a point of no return beyond which nothing can escape. But some theoretical models suggest that under extreme conditions, it might be possible for a singularity to exist without this boundary, exposing its inner workings to the outside universe. If such objects were present in the early cosmos, they could completely change our understanding of how black holes behave and how they interact with their surroundings. Another strange idea is that some of the first black holes might not be black holes at all, but instead, gravastars, hypothetical objects that mimic black holes but have no singularity at their core. Instead, they would be made of exotic matter that resists collapse, creating an ultra-dense object that looks like a black hole from the outside but behaves very differently on the inside. If any of the early quasars turn out to be gravastars, it would shake the foundations of modern astrophysics. And then there's the question of dark matter. We know that dark matter makes up most of the universe's mass, but we still don't know what it actually is. Some theories suggest that dark matter could be made up of primordial black holes, ancient remnants from the earliest moments of the cosmos. If true, this would mean that the search for the first quasars is not just about understanding black holes. It's also about solving one of the biggest mysteries in all of physics. As we continue to search for the first quasars, we are venturing into a realm of the universe that is still largely unknown. Every new discovery brings us closer to answering fundamental questions about how the cosmos evolved, but it also raises new mysteries that challenge our understanding. With new telescopes coming online, new technologies being developed, and new theories being tested, we are on the edge of a new era of discovery, one that could rewrite everything we know about the early universe. The first quasars are more than just distant beacons of light. They are cosmic time capsules, holding the secrets of the universe's infancy. And as we continue to search for them, we are not just uncovering the past, we are revealing the forces that shape the cosmos, the origins of galaxies, and perhaps even the ultimate fate of the universe itself. The journey is far from over, and the biggest discoveries may still be ahead. With every new telescope that peers into the depths of space, with every new quasar that is found, we come one step closer to understanding the origins of everything we see around us. The search for the first quasars is not just a scientific quest, it is a journey into the unknown, a story that is still being written, and one that will continue to shape our understanding of the universe for generations to come. The search for the first quasars is not just about looking deeper into space, it's about unlocking the fundamental processes that shaped the early universe. Every quasar we find from the distant past is a clue, an ancient fossil of light carrying information about an era we can never physically visit. And yet, even with all our advanced technology, we are still struggling to fully understand how these monstrous black holes managed to form so quickly. One of the most perplexing mysteries surrounding early quasars is the presence of extremely massive black holes in the first few 100 million years of the universe. Based on our current understanding of how black holes grow, this shouldn't be possible. Black holes gain mass primarily through accretion, the process of pulling in surrounding gas and dust. But there's a problem. Accretion is limited by a process called the Eddington limit. This is the point at which the outward pressure of radiation from the infalling material balances the gravitational pull of the black hole, preventing it from growing any faster. Yet, somehow, the first quasars must have defied this limit. These early black holes didn't just grow, they exploded in size, reaching billions of times the mass of the Sun in a cosmic blink of an eye. How did they do it? Did they form from direct collapse, skipping the star formation stage entirely? Did they experience episodes of super Eddington accretion, where they rapidly consumed matter at an accelerated rate? Or is there something fundamental about black holes that we still don't understand? Astronomers have been searching for answers in the faint glow of the earliest quasars, but the problem is that these objects are incredibly difficult to observe. Because they are so far away, their light has been stretched by the expansion of the universe, shifting into infrared wavelengths. This is where telescopes like the James Webb Space Telescope, JWST, come in. With its powerful infrared vision, JWST has the capability to peer deeper into the universe than ever before, revealing the earliest quasars with unprecedented clarity. Already, JWST has begun challenging our understanding of the early cosmos. Observations have uncovered galaxies that seem to have formed much earlier than expected, suggesting that star formation may have begun sooner than we thought. If quasars followed a similar pattern, it could mean that black holes started growing in ways we don't yet fully understand. But even more surprising is the possibility that we may have completely underestimated the number of quasars in the early universe. One of the biggest surprises in recent years has been the discovery of faint quasars, objects that were previously hidden from our view because they weren't as bright as the most well-known examples. These dim quasars suggest that there may have been many more black holes forming in the early universe than we originally thought. If this is true, then our models of cosmic evolution may need to be rewritten. But there's another possibility, one that is even more mysterious. What if some of these early black holes never became quasars at all? Instead of growing into bright, energetic objects, some may have remained hidden, lurking in the depths of space as dark, invisible giants. These dark quasars would be incredibly difficult to detect because they don't emit the same high-energy radiation as their more active counterparts. If they exist, they could help explain why we see so many massive black holes in the present-day universe. Because they were there all along, silently growing without ever becoming visible. The existence of dark quasars raises an even bigger question. Could we be missing an entire population of ancient black holes? If so, how would we find them? One idea is that they might be detectable through gravitational lensing, the phenomenon where the gravity of a massive object bends and magnifies the light of objects behind it. If a hidden quasar happens to pass in front of a distant galaxy, it could momentarily reveal itself through this lensing effect. Another potential method is through gravitational waves, ripples in spacetime caused by the collisions of massive objects. If early black holes were merging frequently in the young universe, they may have left behind a detectable gravitational wave signal. The upcoming Laser Interferometer Space Antenna, LISA, mission, set to launch in the 2030s, may be able to detect these ancient signals, providing new insights into the first black holes. As we push further into the unknown, we are beginning to realize that the story of the first quasars is far more complex than we ever imagined. These objects are not just relics of the past. They are active participants in shaping the universe. Their powerful outflows may have influenced the formation of galaxies, regulating star formation and even playing a role in the distribution of dark matter. But perhaps the biggest mystery of all is what the existence of early quasars tells us about the nature of black holes themselves. Our current understanding of black holes is based on Einstein's general theory of relativity, which predicts that every black hole has an event horizon, a point beyond which nothing can escape. However, some physicists have suggested that the first quasars may exhibit behaviors that challenge this idea. One controversial theory proposes that some early black holes may not be true black holes at all, but instead objects known as fuzzballs. In this model, the event horizon is replaced by a complex, string-like structure predicted by string theory. If true, this would mean that black holes are not simple, featureless points in space, but rather highly complex objects with intricate internal structures. Another possibility is that the first quasars could be wormholes, hypothetical tunnels in spacetime that connect different regions of the universe. If any of the early quasars turn out to exhibit unusual gravitational signatures, it could be evidence that some of these objects are not black holes at all, but rather exotic space-time structures unlike anything we've ever seen. These ideas may seem speculative, but the more we learn about the first quasars, the more we are forced to question our assumptions about black holes. Could it be that our entire understanding of black holes is incomplete? Are there hidden laws of physics waiting to be discovered in the extreme environments of these ancient objects? The search for the first quasars is not just a quest to understand the past, it is a journey into the very limits of what we know about the universe. With every new telescope, every new observation, and every new discovery, we are rewriting the story of cosmic evolution. We are uncovering secrets that have been buried for billions of years, and we are slowly piecing together the puzzle of how everything we see today came to be. But there is still so much more to uncover. The first quasars are just the beginning. As we continue to probe deeper into the cosmos, we may find even stranger objects lurking in the darkness, objects that challenge everything we thought we knew about space, time, and the fundamental nature of reality itself. And so, the search continues. The universe is vast, and its mysteries are endless. But with every new discovery, we take one step closer to understanding our place in the grand cosmic story. The journey is far from over, and the greatest revelations may still be ahead. The deeper we dive into the search for the first quasars, the more we realize that these cosmic beacons may be holding the answers to some of the biggest mysteries in astrophysics. One of the most pressing questions is, how did these supermassive black holes form in such a short amount of time? Our current understanding of black hole formation suggests that they should have taken billions of years to grow to the sizes we observe in the early universe. And yet, quasars that existed less than a billion years after the Big Bang already had black holes with masses equivalent to billions of suns. This raises the possibility that black holes in the early universe may have formed through mechanisms we don't yet fully understand. One of the leading theories is the direct collapse model. According to this idea, instead of forming from the remnants of massive stars, some of the first black holes may have formed directly from the collapse of enormous gas clouds. These clouds, composed primarily of hydrogen and helium, may have collapsed under their own gravity without first forming stars. If this process occurred, it could explain how some black holes started their existence with masses thousands of times greater than the Sun, allowing them to grow into supermassive black holes much faster than if they had formed from regular stellar remnants. However, there's another theory that challenges this idea. Some researchers believe that early black holes may have formed through rapid and chaotic mergers of smaller black holes. In this scenario, instead of starting as massive seeds, black holes could have started small and then grown quickly by colliding and merging with other black holes in dense environments. This process, known as hierarchical black hole growth, could have been accelerated in regions of the universe where matter was highly concentrated. But there's another problem. If these black holes were forming so quickly, they should have also been producing enormous amounts of radiation. The light from the surrounding gas being pulled into the black holes should have created powerful radiation pressure, which would normally slow down the black hole's growth. This brings us back to the mystery of super-Eddington accretion. The idea that some black holes may have been able to consume matter at rates far higher than what traditional physics allows. If early quasars were somehow bypassing the normal growth limits, it could explain how they became so massive in such a short time. To test these theories, astronomers have been searching for more quasars in the early universe. But finding them is no easy task. The light from these objects has traveled for billions of years to reach us, meaning it has been stretched into infrared wavelengths due to the expansion of the universe. This makes them incredibly difficult to detect with traditional telescopes. However, with the James Webb Space Telescope, JWST, scientists now have a tool powerful enough to identify some of the most distant quasars ever seen. Already, JWST has revealed new insights that are challenging previous assumptions. Observations have suggested that some quasars may have been surrounded by unexpected amounts of dust, indicating that the first galaxies may have contained far more complex environments than previously thought. This dust could have played a crucial role in feeding early black holes, providing the necessary material for rapid growth. But there's something even stranger lurking in the data. Some researchers believe that the first quasars may not have been isolated objects but part of larger structures, massive clusters of galaxies forming around them. If true, this would mean that the early universe was far more interconnected than we imagined, with quasars acting as the gravitational centers of enormous cosmic structures. Even more intriguing is the possibility that some of the earliest quasars may have interacted with dark matter in unexpected ways. Dark matter, the mysterious substance that makes up most of the universe's mass, does not emit or absorb light, making it invisible to traditional telescopes. However, its gravitational influence is undeniable. Some scientists speculate that dark matter may have played a crucial role in the formation of the first quasars, providing the additional gravitational pull needed to accelerate the growth of early black holes. This raises an even deeper question. Could quasars themselves help us uncover the true nature of dark matter? Some theories suggest that certain types of dark matter may have interacted with the gas surrounding early black holes, potentially altering their growth rates or even affecting their radiation output. If we can detect subtle anomalies in the light from early quasars, we may be able to uncover new clues about the nature of dark matter, one of the biggest unsolved mysteries in physics. But there's another mystery lurking in the search for the first quasars, one that could have profound implications for our understanding of the universe. What if some of the quasars we think we've detected aren't actually black holes at all? Some physicists have proposed that certain high-energy objects in the early universe could have been something entirely different, perhaps even remnants of a previous cosmic cycle. One radical idea is that some of these objects could be primordial wormholes, tunnels in spacetime that connect different regions of the universe. If these wormholes existed in the early cosmos, they might have behaved similarly to quasars, emitting massive amounts of energy as matter fell into them. While this idea remains highly speculative, it raises a fascinating possibility. Could some of the quasars we see today actually be windows into other regions of the universe? Another possibility is that some of these early black holes could be remnants of an entirely different process, one that predates the formation of stars and galaxies. Some theories suggest that certain black holes may have formed directly from fluctuations in the density of the universe shortly after the Big Bang. These so-called primordial black holes would be fundamentally different from those formed through the collapse of stars. If they exist, they could explain some of the unexplained gravitational effects we observe in the universe today. The search for the first quasars is revealing more than just the history of black holes. It is forcing us to confront some of the biggest questions about the nature of space and time itself. Could these ancient objects hold the key to understanding the fundamental laws of the universe? Are we on the verge of discovering new physics that could change our understanding of reality? One thing is clear: the deeper we look, the more mysterious the universe becomes. Every new discovery brings more questions, and the search for the first quasars is far from over. As telescopes become more advanced, we will continue to push the boundaries of what we can observe, revealing even more about these enigmatic objects. And perhaps, one day, we will finally have the answers to the mysteries that have puzzled scientists for decades. But for now, the search continues, and the universe remains as mysterious as ever. The search for the first quasars is not just about understanding black holes. It's about unlocking the secrets of the early universe itself. When we peer back to the time of the first quasars, we are looking at an era known as the Cosmic Dawn, the period when the first galaxies, stars, and black holes were forming. This was a time of chaos, where the fabric of the universe was being shaped into the vast structures we see today. One of the biggest questions tied to quasars is how they influence the process of cosmic reionization. Right after the Big Bang, the universe was filled with a dense, hot plasma of charged particles. As the universe expanded and cooled, these particles combined to form neutral hydrogen, plunging the cosmos into what scientists call the cosmic dark ages. a time when no light could travel freely through space. But something happened to break this darkness. Within the first billion years after the Big Bang, radiation from the first stars, galaxies, and quasars began to ionize this hydrogen, allowing light to travel freely once again. Quasars are thought to have played a major role in this process. Their intense radiation could have helped reionize the surrounding gas, transforming the structure of the universe and allowing galaxies to grow. But how much of a role did they really play? Did quasars alone provide enough energy to reionize the universe, or were other sources, like the first massive stars, equally responsible? This is a debate that continues to this day, and finding more early quasars could help answer this question. One of the strangest discoveries in recent years is that some of the earliest quasars appear to be surrounded by enormous reservoirs of cold gas. This is unusual because, in theory, the intense radiation from these quasars should have heated and blown away much of the surrounding material. Instead, astronomers are finding evidence that some of these ancient black holes were embedded in massive clouds of cold hydrogen, providing an unexpected fuel source that may have allowed them to grow so quickly. Even more surprising is that some early quasars appear to have unusual chemical compositions. Normally, as stars live and die, they produce heavier elements like carbon, oxygen, and iron, which get mixed into the gas of galaxies over time. But some of the first quasars seem to have formed in environments that lack these heavier elements, meaning they may have been surrounded by gas that was almost entirely composed of hydrogen and helium, the same elements that existed right after the Big Bang. This suggests that these quasars were among the first objects to form in the universe, existing before enough stars had lived and died to enrich their surroundings with heavier elements. But here's where things get even stranger. Some quasars appear to have incredibly high concentrations of certain elements, like magnesium and silicon, which shouldn't have existed in such large amounts so early in the universe. This could mean that the first generations of stars formed and died much faster than we thought, producing these elements at an accelerated rate. Or, it could mean that some unknown process in the early universe was responsible for creating these heavy elements, something we don't yet understand. Then there's the mystery of the quasar host galaxies. Every quasar exists at the center of a galaxy, but finding these galaxies is incredibly difficult. The light from the quasar itself is so bright that it drowns out the faint glow of the surrounding stars, making it nearly impossible to observe the galaxy directly. However, with the James Webb Space Telescope, astronomers are beginning to detect the galaxies hosting these quasars, and what they're finding is surprising. Some of these galaxies appear to be far more developed than expected, containing large numbers of stars and complex structures, which shouldn't have been possible so soon after the Big Bang. This challenges our understanding of how galaxies formed and evolved in the early universe. Even more puzzling, some quasars seem to exist in unusually isolated environments, far from other galaxies or sources of matter. This is odd because quasars require enormous amounts of gas to fuel their activity. If they existed in empty regions of space, where did this gas come from? One possibility is that these quasars formed from the direct collapse of massive gas clouds, but another, more exotic idea is that they may have been fed by invisible streams of dark matter. Some theories suggest that dark matter may have funneled gas into these early black holes, providing the material needed for them to grow rapidly. If true, this would be a groundbreaking discovery, linking quasars directly to the mysterious force shaping the large-scale structure of the universe. But there's yet another layer to this mystery. Some researchers believe that the first quasars could be connected to the concept of cosmic voids, vast, empty regions of space that contain very few galaxies. These voids are some of the strangest structures in the universe, and their origins are still not fully understood. Could the first quasars have played a role in their formation? Or were they instead drawn to the dense filaments of matter that connect galaxies in the cosmic web? All of these questions point to a fundamental truth. The first quasars are more than just black holes. They are cosmic time capsules, revealing the physics of the early universe in ways we never imagined. Each new discovery forces us to rethink our theories, pushing the boundaries of what we know about the cosmos. As we continue to search for the most ancient quasars, we may uncover answers to some of the deepest mysteries in physics. Could these objects help us understand the nature of dark matter? Could they reveal new physics beyond Einstein's theories? Or could they even hint at the existence of previous cosmic cycles, suggesting that our universe is not the first, but one of many in an endless cycle of birth and rebirth? The search is far from over, and with every new telescope, we push further into the unknown. The universe has always been full of surprises, and the first quasars may hold the key to some of its greatest secrets. As we continue to look deeper into space, we may be on the verge of discoveries that could change our understanding of reality itself. The search for the first quasars is not just about peering into the distant past, it's about understanding the fundamental forces that shape the universe as we know it today. Every quasar we discover is like a lighthouse from the early cosmos, revealing clues about how the first galaxies formed, how black holes grew, and how the structure of the universe emerged from the chaotic aftermath of the Big Bang. But there's still so much we don't understand, and every new observation seems to raise more questions than answers. One of the biggest mysteries surrounding early quasars is the apparent contradiction between their size and age. The standard model of cosmology suggests that black holes should grow relatively slowly, accreting matter over billions of years before reaching the immense sizes we see today. But the first quasars, some of which existed just a few 100 million years after the Big Bang, appear to have reached supermassive proportions incredibly quickly. Some of these early black holes are billions of times more massive than the Sun, which defies our current understanding of black hole growth. There are a few possible explanations for this anomaly. One idea is that the first black holes formed from the direct collapse of massive gas clouds, skipping the usual process of stellar formation and collapse. Instead of starting as small remnants of dead stars, these direct collapse black holes may have formed with masses hundreds of thousands of times that of the Sun, giving them a significant head start in their growth. This could explain how they managed to reach such enormous sizes so early in cosmic history. Another possibility is that early black holes grew at an accelerated rate due to unusually efficient accretion. Normally, a black hole can only consume matter at a certain rate, limited by the so-called Eddington limit, which describes the balance between the inward pull of gravity and the outward pressure of radiation from the accretion disk. However, if the first quasars were surrounded by dense, cold gas, they may have been able to sustain super Eddington accretion, allowing them to grow far more rapidly than expected. But there's another, more radical possibility, one that challenges our entire understanding of physics. Some researchers have proposed that the first quasars may be evidence of new, unknown mechanisms of black hole formation that don't fit within the standard model of astrophysics. Could it be that the laws of physics work differently in the early universe? Could there be exotic types of matter or undiscovered forces that allowed these black holes to form and grow at unprecedented rates? One of the most intriguing hypotheses suggests that some of the first quasars may not have formed from ordinary matter at all. Instead, they could be primordial black holes, hypothetical objects that may have formed in the extreme conditions of the Big Bang itself. Unlike black holes that formed from collapsing stars, primordial black holes could have originated from fluctuations in the density of the early universe, collapsing directly under their own gravity before any stars or galaxies even existed. If true, this would not only explain the existence of early quasars, but it could also provide a potential solution to another major cosmic mystery, the nature of dark matter. Some theories suggest that primordial black holes could make up a significant portion of the universe's dark matter, the invisible substance that accounts for most of the mass in the cosmos. If the first quasars were actually clusters of these primordial black holes merging together, it could explain their rapid growth and unusual properties. But detecting primordial black holes is incredibly difficult, and so far, there is no definitive evidence proving their existence. Still, the idea that quasars could be connected to dark matter is an exciting one. Dark matter is one of the biggest mysteries in physics, an invisible force that shapes galaxies, bends light, and governs the motion of the universe on the largest scales. If quasars are somehow linked to dark matter, it could mean that these ancient black holes are not just relics of the past, but active participants in the cosmic story of how galaxies formed and evolved. But there's another mystery that makes the first quasars even more perplexing, their alignment. Recent studies have suggested that some quasars appear to be aligned with each other across vast cosmic distances, a phenomenon that shouldn't be possible under our current understanding of physics. In theory, quasars that are billions of light years apart should be randomly oriented, with no connection to one another. But observations have shown that their spin axes seem to be mysteriously correlated, hinting at some unknown large-scale structure in the universe that we don't yet understand. Could this be evidence of hidden cosmic forces at play? Some scientists speculate that these alignments could be the result of primordial magnetic fields, remnants of the early universe that have influenced the formation of galaxies and black holes over billions of years. Others suggest that it could be evidence of deeper, fundamental connections between quasars, perhaps linked to the fabric of spacetime itself. And then there's the question of quasar variability. While quasars are typically thought of as stable beacons of light, recent observations have shown that some of them can change their brightness dramatically over short periods of time. In some cases, quasars have been observed to dim or brighten by factors of 10 or more within just a few years, a phenomenon that shouldn't be possible given the immense size of these objects. One explanation is that these changes are caused by fluctuations in the accretion disk, as material falls into the black hole in bursts rather than in a steady stream. But some astronomers have proposed a more exotic possibility, that these brightness changes could be caused by interactions with unseen objects, such as intermediate mass black holes or even hypothetical exotic particles that affect the flow of matter into the quasar. And what about the possibility of hidden quasars? While we've discovered thousands of quasars, there may be many more lurking in the shadows, obscured by thick clouds of dust and gas that prevent their light from reaching us. These hidden quasars could be key to understanding how black holes grow and evolve in different environments, and new telescopes like the James Webb Space Telescope are designed to peer through these cosmic veils, revealing what lies beyond. The search for the first quasars is far from over. Every new discovery brings us closer to understanding the origins of the universe, but it also reveals new questions that challenge our understanding of physics and cosmology. Could quasars hold the key to understanding dark matter? Are they evidence of unknown cosmic forces that shape the early universe? Or do they hint at entirely new physics that we have yet to discover? As we continue to push the boundaries of what we can observe, one thing is clear: the universe is far more complex and mysterious than we ever imagined. And somewhere out there, hidden in the depths of space, the answers to some of our biggest questions are waiting to be found. The deeper we dive into the mystery of the first quasars, the more we realize how much remains unknown. These cosmic beacons defy our expectations, forcing us to reconsider everything we thought we knew about black holes, galaxy formation, and even the fundamental laws that govern the universe. Every new quasar discovered pushes our understanding further, revealing an ancient era where the cosmos was still taking shape. But what if the first quasars aren't just remnants of the past? What if they are active participants in a grand cosmic puzzle that extends far beyond our current comprehension? One of the most perplexing questions surrounding quasars is their relationship with the large-scale structure of the universe. Modern cosmology tells us that the universe is not randomly arranged but follows a vast, interconnected web known as the cosmic web. This structure consists of enormous filaments of galaxies stretching across billions of light years, with vast voids of empty space in between. But here's where things get strange. Some of the first quasars appear to be positioned in ways that align with these cosmic filaments, suggesting a deeper connection between black holes and the very framework of the universe. This discovery raises several intriguing possibilities. Could the formation of supermassive black holes be influenced by the cosmic web itself? Are these structures acting as conduits for the rapid growth of black holes, funneling matter toward them in ways we don't yet understand? If so, this could help explain how the first quasars reached such immense sizes so quickly. Perhaps they weren't forming in isolation, but were instead part of a much larger and more complex cosmic dance. And then there's the question of what came before the first quasars. If quasars represent some of the earliest black holes in the universe, what were their immediate predecessors? Some researchers believe that the very first black holes may have formed not from stars, but from the collapse of exotic matter that existed in the high-energy chaos of the early universe. Others suggest that these objects could have formed in the aftermath of violent cosmic events, perhaps even the merging of primordial black holes that originated in the first moments after the Big Bang. If this is true, it could change everything we know about the early universe. It would suggest that black holes, and by extension quasars, played a crucial role in shaping the cosmos from the very beginning, rather than being a byproduct of galaxy formation. This could mean that black holes aren't just endpoints of stellar life, but fundamental building blocks of the universe itself. But if quasars are so deeply connected to the formation of the universe, could they also provide insights into its ultimate fate? Some theories suggest that black holes could hold the key to understanding how the cosmos will end. If the universe continues to expand indefinitely, could quasars one day fade away, leaving behind only cold, lifeless remnants? Or could they instead play a role in the eventual collapse of the universe, pulling matter back together in ways we don't yet understand? Some scientists even speculate that quasars might be linked to the nature of dark energy, the mysterious force driving the accelerating expansion of the universe. If there is a deeper connection between quasars and the fabric of spacetime, then studying them could reveal clues about the fundamental forces shaping reality itself. Could quasars be tapping into some unknown energy source that influences the universe on a grand scale? Or do they represent evidence of hidden dimensions or exotic physics that go beyond our current theories? One of the strangest possibilities is that the first quasars could be signs of something even more profound, perhaps even evidence of previous universes. Some cosmologists believe that black holes might be more than just gravitational sinks. They could be doorways to new regions of space-time, or even entire new universes. If so, the first quasars could be remnants of a previous cosmic cycle, carrying information from an era before our universe even existed. This idea is speculative, but it raises fascinating questions. If quasars are connected to the fundamental structure of reality, could they provide hints about the true nature of the multiverse? Could their bizarre properties be evidence of interactions with other dimensions, or even messages from an earlier cosmos? The search for the first quasars is not just about understanding the distant past, it's about unlocking the deepest secrets of the universe. Each new discovery brings us closer to answering questions that have puzzled scientists for decades. How did the first black holes form? What role did they play in shaping the cosmos? And what do they tell us about the ultimate fate of the universe? But perhaps the most exciting part of this search is that we are still only scratching the surface. With new telescopes and advanced observational techniques, we are now able to look further into the universe than ever before, revealing details that were once thought to be beyond our reach. And as we continue to push the limits of what we can see, we may find that the mysteries of the first quasars are even stranger than we ever imagined. What if the first quasars are not just relics of the past, but keys to understanding the deepest mysteries of the cosmos? What if they hold the answers to questions we haven't even thought to ask yet? As we continue to explore the universe, one thing is certain: the search for the first quasars is far from over, and the discoveries waiting to be made may change everything we thought we knew about the nature of reality itself. The search for the first quasars is more than just an investigation into the distant past. It's a journey toward understanding the very foundations of reality. Every step we take in this exploration challenges our assumptions about the early universe, black holes, and the vast cosmic structures that emerged from the chaos of the Big Bang. But there's another angle to this mystery, one that's rarely considered. What if we've been looking at quasars the wrong way? For decades, scientists have assumed that quasars are simply black holes at the hearts of galaxies, feeding on matter and lighting up the universe with their incredible energy. But some researchers have begun to ask a radical question: what if quasars aren't just black holes? What if there's something else entirely, something we haven't even considered? One of the strangest ideas to emerge in recent years is that quasars might be connected to wormholes, hypothetical tunnels through spacetime that could link different regions of the universe, or even different universes altogether. If this is the case, then quasars might not just be feeding on nearby gas and dust. They could be drawing in matter from entirely different parts of the cosmos. This would explain some of the bizarre properties of quasars that don't quite fit with our current understanding of black holes. For example, some quasars appear to have brightness fluctuations that don't match what we would expect from a black hole simply consuming matter. Could these changes be the result of matter flowing in from another region of the universe? And if quasars are connected to wormholes, then what happens to the matter that gets pulled in? Does it simply disappear into another part of space, or does it emerge somewhere else as an outflow of energy? Some theories suggest that the opposite end of a quasar might be something called a white hole, a hypothetical object that expels matter rather than consuming it. If this is true, then quasars might be part of a vast, hidden network of cosmic tunnels that transport energy and matter across unimaginable distances. But the idea of quasars being more than just black holes gets even stranger. Some researchers have suggested that quasars might not be objects at all, but instead cosmic events, temporary phenomena caused by the interaction of exotic physics that we don't yet understand. What if quasars are signs of quantum fluctuations on a massive scale, where space and time itself are being reshaped in ways we can't yet comprehend? This would mean that quasars aren't just windows into the past, but active players in the evolution of the universe. They could be influencing the way galaxies form, shaping the movement of cosmic structures, and even affecting the fundamental forces of physics. Could quasars be part of some deeper, hidden process that drives the expansion and evolution of the universe? And then there's the possibility that quasars might not be from our universe at all. Some scientists have proposed that the first quasars could be remnants of a previous cosmic cycle, leftovers from a universe that existed before the Big Bang. If the universe is part of an endless cycle of expansion and collapse, then quasars might be evidence of the last moments of a previous cosmos, somehow surviving into our own. If this is the case, then quasars could be carrying information from a time before time itself. Could they contain the remnants of physical laws that no longer exist? Could they be the echoes of an entirely different kind of physics, one that shaped a universe before ours? If we could decode the signals from the first quasars, could we uncover secrets about the true nature of reality? The deeper we go into this mystery, the more we realize how much we don't know. The first quasars are unlike anything else in the universe, and every new discovery raises more questions than answers. But one thing is clear: whatever quasars are, they are far more than just distant points of light. They are cosmic enigmas, defying explanation and challenging our understanding of space, time, and the very fabric of reality itself. The search for the first quasars is just beginning, and the mysteries they hold may change everything we know about the universe. As telescopes grow more powerful and new discoveries emerge, we may finally begin to unravel the secrets of these ancient objects. But until then, one question remains: are quasars just the beacons of the early universe? Or are they something far stranger, something that could redefine our understanding of existence itself? If quasars are more than just black holes feeding on cosmic debris, then what exactly are we looking at? Could they be remnants of a time when the laws of physics were different? Or are they signals from processes so extreme that we haven't even begun to comprehend their true nature? Every new quasar discovered adds another piece to the puzzle, yet the picture remains incomplete. One of the strangest aspects of the first quasars is their sheer brightness. They are so luminous that they outshine entire galaxies, making them visible across billions of light years. But this presents a paradox. If a quasar is powered by a supermassive black hole consuming matter, then why are some quasars so much brighter than others? And why do some appear to have formed so early, when the universe was still in its infancy? The brightness of a quasar depends on the amount of material falling into its black hole. The more gas and dust it consumes, the more energy it releases. But some quasars seem to be consuming matter at a rate that defies our current models. If black holes have an upper limit on how fast they can grow, called the Eddington limit, then how did the first quasars reach such enormous sizes in such a short time? One theory suggests that the early universe was more chaotic than we thought, with dense regions of gas collapsing directly into massive black holes without first forming stars. If true, this would mean that some of the first black holes didn't start small and gradually grow, but instead formed almost fully grown, ready to become quasars right away. Another possibility is that these early quasars had access to an unusual feeding mechanism, perhaps an inflow of matter from cosmic filaments, channels of gas that extend across the universe like highways of material leading directly to black holes. If quasars were positioned at the intersections of these filaments, they could have been pulling in matter from vast distances, growing at astonishing rates. But even this doesn't fully explain their extreme brightness. Some researchers have proposed that quasars could be tapping into unknown energy sources, perhaps even drawing energy directly from the structure of space-time itself. This idea, though speculative, raises fascinating questions. Could quasars be connected to exotic physics that we haven't yet discovered? Could they be interacting with dark matter or dark energy in ways we don't yet understand? Dark matter and dark energy make up most of the universe, yet we know almost nothing about them. If quasars have some unknown link to these mysterious forces, they could be key to unlocking some of the greatest unsolved mysteries in cosmology. Could quasars be amplifying dark energy, accelerating the expansion of the universe? Or could they be revealing hidden aspects of dark matter, showing us how it behaves under extreme conditions? And then there's the possibility that quasars could be gateways, portals to new physics or even new realities. Some scientists have speculated that quasars might be evidence of cosmic strings, hypothetical defects in spacetime that could stretch across the universe. If quasars are connected to these structures, they could be revealing evidence of higher dimensions or unknown aspects of gravity. This idea isn't as far-fetched as it might seem. Some theories suggest that black holes could be connected to other parts of the universe through wormholes. If quasars are somehow linked to these structures, they might not just be consuming matter, they could be transporting it elsewhere. Could quasars be acting as one-way exits, expelling energy into another region of space? Or could they be part of a larger network of hidden cosmic structures that we haven't even begun to map? As we search for the first quasars, we are confronted with questions that go beyond astronomy. We are looking at objects so old and so extreme that they challenge the very foundations of physics. Every quasar we discover is a glimpse into a universe that was vastly different from the one we see today. Were the laws of nature the same back then? Or are we witnessing the remnants of a different cosmic order, one that no longer exists? The more we learn about quasars, the more they seem to hint at something deeper, a hidden layer of reality that we are only beginning to uncover. Are quasars just ancient relics of the early universe? Or are they signs of something much stranger, something that could change our understanding of the cosmos forever? The search for answers continues, and with every new discovery, we move one step closer to unlocking the greatest mysteries of the universe. But perhaps the most exciting possibility is that the quasars we've found so far are just the beginning. What if there are even more extreme objects out there, waiting to be discovered? What if the strangest quasars are yet to come? If the first quasars challenge our understanding of how black holes formed in the early universe, then what does that say about the structure of the cosmos itself? We've assumed that the universe evolved in a fairly predictable way, starting with a hot, dense state after the Big Bang, cooling over time, forming the first stars and galaxies, and eventually giving rise to the cosmic web we see today. But the discovery of ancient quasars throws a wrench into this timeline. Quasars are powered by supermassive black holes, some of which are billions of times more massive than the Sun. But how did they grow so fast? The universe was only a few 100 million years old when the first quasars appeared. That's a blink of an eye in cosmic terms. If black holes take time to grow, then these quasars shouldn't exist, at least not according to our current models. One possible explanation is that the first quasars weren't like the black holes we see today. Instead of forming from collapsed stars, they may have originated from massive gas clouds that collapsed directly into black holes, bypassing the usual star-forming process. This would allow them to grow rapidly, reaching enormous sizes in a short period of time. But even this idea has problems. If these black holes formed so quickly, they should have left behind signatures, traces of their rapid birth that we should be able to detect. Yet, so far, the evidence remains elusive. Could it be that the first quasars were powered by something other than gravity? Some scientists have proposed that the early universe may have been filled with dense pockets of exotic matter, substances that don't exist under normal conditions today. If this is true, then the first black holes might have grown by feeding on this strange material, accelerating their growth in ways we don't yet understand. Others have suggested that dark matter itself may have played a role. If dark matter interacted with itself in ways we haven't yet observed, then it could have clumped together, forming the seeds of the first supermassive black holes. This would mean that dark matter isn't just an invisible component of the universe. It might have actively shaped the evolution of galaxies and quasars. But what if there's an even stranger possibility? Some theories propose that the first quasars might be remnants of a universe that existed before our own. If the cosmos goes through cycles of expansion and collapse, then the first quasars could be fossils from a previous iteration of reality, leftovers from a time before the Big Bang. If this is the case, then quasars might be more than just cosmic lighthouses. They could be time capsules, holding information about the fundamental nature of existence itself. Could they contain clues about the physics of a universe that no longer exists? Could they reveal secrets about forces that shaped reality before our own era began? The deeper we look, the more we realize how much we don't know. Every new quasar discovered is another piece of the puzzle, yet the picture remains incomplete. Are we seeing the birth of the first black holes, or are we witnessing something much stranger, something that hints at a deeper cosmic mystery? With each discovery, we get closer to understanding the nature of quasars. But at the same time, they continue to defy explanation, raising new questions with every answer we find. What are quasars really telling us about the universe? And could they be the key to unlocking some of the deepest secrets of existence? The mystery of the first quasars goes beyond just their brightness and mass. It forces us to rethink the early universe itself. When we look at these ancient beacons of light, we aren't just seeing black holes consuming matter. We are seeing a time when the universe was barely a few 100 million years old, a time when stars were just beginning to form, and yet, somehow, these supermassive black holes already existed. This defies our current understanding of cosmic evolution. Black holes are supposed to take time to grow, accreting material slowly over billions of years. But the first quasars are billions of times more massive than the Sun, and they existed when the universe was still in its infancy. This raises one of the biggest paradoxes in modern astrophysics. How did these black holes grow so quickly? One explanation is that they formed from the direct collapse of massive gas clouds, skipping the normal black hole formation process that involves the death of stars. Instead of starting small and gradually gaining mass, these black holes may have been born already millions of times the mass of the Sun. This idea is known as the direct collapse black hole model. And while it helps explain the size of the first quasars, it also raises new questions. For one, if black holes could form this way in the early universe, why don't we see them forming like this today? Is it because the conditions of the early universe were fundamentally different, allowing for direct collapse in a way that's no longer possible? Or are we missing something even bigger, some hidden factor that allowed these quasars to grow at an unprecedented rate? Some scientists have speculated that the first black holes may have been able to feed much faster than we previously thought. Normally, when a black hole consumes matter, the energy released creates a powerful outward force, radiation pressure, that pushes material away, effectively limiting how fast the black hole can grow. This is known as the Eddington limit. However, some researchers believe that the first quasars may have been able to exceed this limit, growing at rates we didn't think were possible. If this is true, it means our understanding of black hole physics might be incomplete. Are there ways for black holes to grow beyond the Eddington limit without disrupting their own accretion disks? Could they have been fed by vast streams of gas flowing directly into them, avoiding the usual choking effects of radiation pressure? Another possibility is that the first black holes didn't just grow by consuming normal matter. They may have had access to a much more exotic fuel source. Some theories suggest that dark matter, the mysterious invisible substance that makes up most of the universe's mass, could have played a role in the formation of the first quasars. If dark matter particles interact with each other in ways we don't yet understand, they might have clumped together, forming dense regions where black holes could rapidly grow. Some models even propose that dark matter could have formed its own type of black holes, ones that don't rely on normal matter at all. If such objects exist, they could explain why the first quasars appeared so early in the universe's history. But there's an even wilder possibility. Some researchers have speculated that the first quasars might not be entirely from our universe. Instead, they could be remnants of a time before the Big Bang, traces of a previous cosmic cycle. If the universe undergoes cycles of expansion and contraction, then some structures from an older era might have survived, appearing to us as ancient quasars. This idea, known as the Cyclic universe theory, suggests that the Big Bang wasn't truly the beginning of everything, but rather just one phase in an endless series of cosmic rebirths. If this is the case, then quasars could be the fingerprints of a universe that came before our own, offering clues about physical laws that existed before our current reality. Could it be that the first quasars are more than just ancient black holes? Could they be gateways to understanding deeper aspects of the universe, hints that reality itself is more complex than we ever imagined? The more we study quasars, the more they defy explanation. Some of the oldest ones have been found at distances so great that their light has taken over 13 billion years to reach us. This means that when we observe them, we are looking at a universe that was less than a billion years old. But if our models of black hole growth are correct, there simply shouldn't have been enough time for these quasars to exist. One particularly perplexing quasar, known as J0313-1806, is one of the most distant and oldest quasars ever discovered. It existed just 670 million years after the Big Bang, and is powered by a black hole with a mass of over 1.6 billion suns. The problem? According to our current understanding of physics, a black hole that massive shouldn't have had enough time to form. Scientists are now scrambling to figure out how these objects could have grown so fast. Some think there might be unknown processes at work, allowing black holes to gain mass much more quickly than expected. Others suggest that these quasars may be revealing something even deeper, something that challenges our entire view of the early universe. Could it be that the laws of physics were slightly different back then? Some theories suggest that fundamental constants, such as the strength of gravity, might have changed over time. If true, this could mean that black holes in the early universe behaved in ways we don't fully understand. Or maybe we are missing something even bigger. Some physicists have suggested that quasars could be linked to extra dimensions, hidden aspects of reality that we can't normally perceive. If these dimensions exist, they could be affecting the growth of black holes in ways we don't yet understand. And then there's the possibility that quasars could be more than just natural phenomena. Some scientists have wondered if these objects could be signs of advanced civilizations, structures so large and powerful that they mimic the behavior of quasars. This might sound far-fetched, but some researchers have considered the idea that highly advanced extraterrestrial civilizations could harness black holes as energy sources, creating artificial quasars in the process. This idea, while speculative, raises fascinating questions. If an advanced civilization wanted to generate enormous amounts of energy, tapping into a black hole would be one of the most efficient ways to do it. Could it be that some quasars are actually the signatures of intelligent life on a scale beyond anything we've ever imagined? At this point, we simply don't know. But the search for the first quasars continues, and with every new discovery, we inch closer to answering one of the greatest mysteries in astrophysics. As new telescopes come online, such as the James Webb Space Telescope and the upcoming Extremely Large Telescope, we will be able to peer deeper into the universe than ever before. These instruments will allow us to study the first quasars in greater detail, potentially revealing their secrets at last. But what will we find? Will we confirm that these ancient black holes grew through natural processes? Or will we uncover something far stranger, evidence that the universe is far more mysterious than we ever imagined? The search for the first quasars is not just a quest to understand the past. It is a journey into the unknown, a journey that could reshape our understanding of reality itself. And perhaps, in the process, we will discover that the greatest cosmic mysteries are still waiting to be solved. The search for the first quasars has already rewritten our understanding of the cosmos, but every new discovery brings more questions than answers. If these supermassive black holes existed so early in the universe's history, then we are forced to rethink not only how black holes form but also how the entire structure of the early universe developed. Were the conditions of the cosmos different back then in ways we don't yet understand? Did black holes emerge in ways completely unlike how they do today? Or could there be unknown forces or hidden physical laws that played a role in their rapid growth? One of the biggest challenges in solving this mystery is that quasars exist at the farthest edges of what we can observe. Because light from these ancient objects takes billions of years to reach us, we are effectively looking back in time when we study them. However, the further we look into the past, the more difficult it becomes to make precise observations. The light from these distant quasars is redshifted, stretched out as the universe expands, making it harder to analyze their properties. But modern technology is catching up. The James Webb Space Telescope, JWST, has already begun probing some of the earliest quasars, providing data that could change our understanding of their origins. Unlike previous telescopes, which were limited in how far they could see, JWST is designed to observe infrared light, allowing it to cut through cosmic dust and see objects that were previously hidden from view. With its advanced capabilities, scientists hope to detect even earlier quasars, possibly ones that formed within the first few 100 million years after the Big Bang. If we find quasars even earlier than expected, it could completely upend our current theories about the early universe. It would suggest that black holes formed much more quickly than we ever thought possible, or that the physics governing the early universe was different from what we assume. Some researchers have even suggested that the discovery of these ancient quasars might provide indirect evidence for exotic theories, like the idea that our universe underwent a rapid period of inflation, or that black holes played a role in shaping the cosmos at a fundamental level. One of the key questions driving this research is, what role did quasars play in the evolution of the universe? These objects weren't just passive observers in the early cosmos, they actively influenced their surroundings. The intense radiation from quasars is powerful enough to ionize gas across entire galaxies, and some scientists believe that these objects played a role in reionizing the universe, the process that transformed the cosmos from being filled with neutral gas to one dominated by ionized plasma. Reionization is one of the biggest unsolved mysteries in cosmology. We know that the universe started out as a hot, dense plasma after the Big Bang, but as it expanded and cooled, this plasma formed neutral hydrogen atoms. For hundreds of millions of years, the universe remained in this neutral state, with no light able to travel freely. But then, something happened, something powerful enough to strip electrons away from hydrogen atoms and turn the universe into a transparent state, allowing light to travel unimpeded. What caused this reionization? Many astrophysicists suspect that quasars played a significant role. Their immense energy output could have provided enough radiation to ionize vast regions of space, contributing to this major cosmic transition. But if quasars were responsible for reionization, then that raises another question: how many of them were there? If early quasars were rare, then they might not have been enough to reionize the entire universe. But if they were more common than we think, then it suggests that supermassive black holes were forming at an astonishing rate, far faster than any of our current models can explain. This leads us to another unsolved mystery: where did all these early quasars go? Today, quasars are much rarer than they were in the past. While we can still find active supermassive black holes at the centers of galaxies, they don't shine nearly as brightly as their ancient counterparts. So what happened to them? Did they run out of material to consume? Did their host galaxies evolve in ways that shut down their activity? Or did they merge with other black holes, creating even larger but less active structures? One possibility is that many of the first quasars eventually merged with one another, forming the supermassive black holes we see at the centers of modern galaxies. The Milky Way, for example, has a supermassive black hole called Sagittarius A*, but it is nowhere near as luminous as the ancient quasars we observe in the distant universe. This suggests that it might have once been an active quasar but eventually calmed down as it exhausted its surrounding material. But here's where things get even stranger. Some astrophysicists have speculated that there might still be fossil quasars hidden in our universe, objects that were once active but are now dormant. If we could find these remnants, we might be able to study them and determine what caused them to turn off. But searching for these hidden quasars is incredibly difficult, as they no longer emit the bright radiation that makes active quasars easy to detect. However, there may be a way to find them. Some researchers believe that gravitational waves, ripples in space-time caused by massive cosmic collisions, could provide clues about the fate of the first quasars. If these objects did merge over time, then they should have produced gravitational waves that we might be able to detect using instruments like LIGO and future gravitational wave observatories. This opens up an entirely new way of studying the universe. Instead of relying solely on light to observe distant objects, we can now use gravitational waves to detect the hidden movements of massive cosmic structures. And if we do find evidence of ancient quasar mergers, it could confirm that these objects played a fundamental role in shaping the structure of the universe as we see it today. But even if we solve the mystery of how the first quasars formed, we still have to answer an even deeper question. Why do black holes exist in the first place? The fact that these objects can grow so massive and influence the universe on such a large scale suggests that they are more than just simple remnants of collapsed stars. Some scientists have even proposed that black holes could be the building blocks of the cosmos itself, acting as seeds for galaxy formation, or even serving as portals to other dimensions. There is even a theory that black holes could be connected to dark matter, the mysterious substance that makes up most of the universe's mass but remains invisible to our instruments. If black holes and dark matter are somehow linked, then the first quasars could hold the key to understanding one of the biggest unsolved mysteries in physics. The search for the first quasars is about more than just studying ancient black holes. It's about uncovering the fundamental laws that govern the universe, answering questions that have puzzled scientists for decades, and perhaps even discovering entirely new aspects of reality. As we continue to push the limits of what we can observe, we may find that the mysteries of quasars are only the beginning of a much deeper cosmic puzzle, one that could change our understanding of the universe forever. And with every new discovery, one thing becomes increasingly clear: the universe is far more mysterious than we ever imagined. The deeper we go into the mystery of the first quasars, the more we realize how much we still don't know. These objects are not just relics of the past. They are key pieces of a puzzle that could redefine everything we understand about black holes, galaxy formation, and even the fundamental laws of physics. But perhaps the most perplexing question of all is this: if quasars existed so early in the universe's history, then how did supermassive black holes, the engines powering them, form so quickly? Our current understanding of black hole formation suggests that they should take billions of years to reach the sizes we see in these early quasars. Typically, black holes form from the remnants of massive stars that explode as supernovae. But this process alone doesn't explain how some of the first quasars we've found have black holes billions of times the mass of the Sun, all within just a few 100 million years after the Big Bang. That's simply too fast for conventional models. So, what's going on? There are several competing theories, and each one challenges our understanding of the early universe. One idea is that these black holes didn't form from regular stars at all but instead emerged from the direct collapse of massive clouds of gas. This process, known as the direct collapse black hole theory, suggests that under the right conditions, an enormous gas cloud could collapse directly into a black hole without ever forming a star. This would allow for much larger black holes to form right away, rather than slowly growing from stellar remnants. Another possibility is that black holes in the early universe grew at an unprecedented rate, far beyond what we see today. Normally, black holes grow by accreting matter, pulling in gas, dust, and even entire stars. However, there's a theoretical limit to how fast this process can happen, called the Eddington limit. If a black hole grows too quickly, the radiation pressure from the infalling matter should push material away, preventing it from gaining mass indefinitely. But some researchers speculate that in the extreme conditions of the early universe, this limit might have been exceeded, allowing black holes to grow much faster than previously thought. There's also the intriguing possibility that black holes may have formed in a way we haven't even considered yet. Some cosmologists have suggested that the first black holes could have originated from fluctuations in the density of the early universe itself, essentially forming primordial black holes that existed before stars and galaxies even came into being. If true, this would mean that black holes weren't just a byproduct of stellar evolution, but fundamental components of the cosmos from the very beginning. If primordial black holes do exist, they could help solve multiple mysteries at once. Not only would they explain the rapid appearance of supermassive black holes, but they could also be a candidate for dark matter, the invisible substance that makes up most of the universe's mass. Some theories suggest that if these early black holes were small enough, they might have survived to the present day as a hidden form of matter that we have yet to detect directly. This would mean that the first quasars aren't just a clue to understanding the early universe. They might also be a key to unraveling one of the biggest cosmic mysteries of all time. The idea that black holes and dark matter could be connected is gaining traction among physicists. If black holes formed directly from dense fluctuations in the early universe, then they might still be lurking everywhere, hidden in plain sight. While we typically think of black holes as massive, star-devouring objects, there could be countless small ones drifting through space, completely invisible except for the gravitational effects they exert on their surroundings. And this brings us to yet another question. If black holes played such a major role in shaping the early universe, could they also influence its ultimate fate? The universe is expanding, but the nature of this expansion is one of the greatest unresolved mysteries in cosmology. Observations suggest that the expansion of the universe is actually accelerating due to an unknown force we call dark energy. But what if black holes, or the remnants of ancient quasars, somehow contribute to this process? Could they be altering the large-scale structure of the cosmos in ways we don't yet understand? Some physicists speculate that the energy stored in black holes could eventually be released in ways we haven't yet discovered. If black holes gradually lose mass over time through a process called Hawking radiation, then what happens when all the supermassive black holes in the universe evaporate? Could they release a final burst of energy that fundamentally changes the universe as we know it? It's possible that the first quasars aren't just ancient relics but instead cosmic time bombs, objects that could have consequences far beyond their lifetimes. The more we study them, the more we realize that these mysterious beacons of the early universe might hold secrets about the past, present, and future of everything. And perhaps the strangest possibility of all is that quasars might not even be what we think they are. While the standard explanation is that they are powered by supermassive black holes, some alternative theories suggest that they could be something entirely different, objects that don't fit into our current understanding of physics at all. For example, some researchers have proposed that quasars might be powered by exotic forms of matter or even entirely new physical phenomena that we haven't yet discovered. If that's the case, then studying quasars could lead to groundbreaking discoveries that go beyond astrophysics, potentially revealing new aspects of reality itself. As technology advances, we are getting closer to unlocking the true nature of these ancient cosmic giants. With telescopes like JWST and upcoming observatories capable of detecting even fainter, more distant quasars, we are on the verge of seeing deeper into the universe than ever before. Every new discovery brings us closer to answering the fundamental questions. How did the first quasars form? What role did they play in shaping the universe? And could they hold the key to understanding the deepest mysteries of existence? The search for the first quasars isn't just about looking at distant objects. It's about peering into the unknown, pushing the boundaries of what we think is possible, and confronting the vast and humbling reality that the universe is still full of secrets waiting to be uncovered. And if history has taught us anything, it's that the answers we find will only lead to even more mind-bending questions. If quasars are the lighthouses of the early universe, then understanding them is like decoding messages from a time when everything was different, when galaxies were just beginning to form, when the cosmic web was still knitting itself together, and when the laws of physics may have operated in ways we still don't fully grasp. The fact that we can see quasars at all is remarkable. Light from these objects has traveled from more than 13 billion years to reach us, meaning we are observing them as they were when the universe was less than a billion years old. But here's the real mind-bending part. If we see a quasar that is 13 billion light-years away, that means the quasar itself no longer exists in the form we're seeing it. This presents a strange paradox. By the time the light from a quasar reaches us, it may have already transformed into something else, such as a normal galaxy with a dormant black hole. What we are seeing is a ghost image of a past reality, a snapshot of a moment that no longer exists. It's as if we are looking back in time through a cosmic time machine, witnessing events that have already played out. This also raises an intriguing question. If quasars were once so common in the early universe, why do we see so few of them today? The answer lies in the life cycle of galaxies. Most astronomers believe that every large galaxy, including our own Milky Way, once had a quasar phase. During this phase, the central black hole was actively devouring matter, creating the extreme brightness that defines a quasar. But over time, as the black hole consumed all the available fuel in its vicinity, the quasar would eventually fade. What remains is a galaxy with a supermassive black hole at its core, but without the high-energy accretion that makes a quasar shine. This means that the Milky Way itself might have once been home to a quasar billions of years ago. In fact, evidence suggests that our galaxy's central black hole, Sagittarius A*, was far more active in the past. Today, it is relatively quiet, but there are signs that it experienced periods of much higher activity, possibly even reaching quasar-like levels for brief periods in cosmic history. If true, then our galaxy was once a blinding beacon in the universe, radiating immense energy before settling into its current, calmer state. But if quasars eventually fade, what happens to their supermassive black holes? This is another puzzle that scientists are trying to solve. We know that black holes continue to exist even after a quasar has shut down, but their long-term evolution is still unclear. Some theories suggest that they continue to grow by merging with other black holes over time, eventually becoming even more massive. Others propose that they slowly lose energy through processes like Hawking radiation, eventually shrinking down over trillions of years. One of the biggest mysteries in astrophysics is whether black holes truly last forever. According to Stephen Hawking's groundbreaking work, black holes should slowly evaporate over time, emitting tiny amounts of radiation in a process known as Hawking radiation. If this is correct, then the black holes left behind by ancient quasars might one day disappear completely. However, the timescale for this process is mind-bogglingly long, far longer than the current age of the universe. This leads to another unsettling thought. If quasars represent the extreme, active phase of black holes, and if black holes themselves might one day vanish, then what does that mean for the fate of the universe? Some physicists have speculated that in the far future, the universe will enter a phase where all that remains are black holes slowly evaporating into nothingness. If that's true, then the quasars we see today might be some of the last traces of a past era, one where the universe was young, energetic, and full of light. But there is yet another possibility, one that challenges everything we think we know about black holes. Some researchers have proposed that black holes might not actually evaporate at all. Instead, they might transform into something even stranger, objects that exist beyond the limits of our current understanding. Some radical theories suggest that the interiors of black holes might not be singularities, as we've long assumed, but rather gateways to new kinds of physics. If true, then quasars might not just be relics of the past. They could be clues to an entirely new branch of science waiting to be uncovered. And here's where things get truly bizarre. Some physicists have speculated that the universe itself might have been born from a black hole. If that's the case, then every quasar we observe might be a glimpse into a process that has repeated countless times across cosmic history. What if quasars are not just markers of the past, but also hints of the future? What if every quasar represents the birth of a new universe, each one spinning off into a reality of its own? This idea, known as the black hole cosmology hypothesis, suggests that what we call the Big Bang might not have been the absolute beginning of everything, but rather the emergence of our universe from a larger cosmic structure. If this is true, then quasars could be more than just distant objects in space. They might be the footprints of a much grander process, one where new universes are being born all the time. It's a staggering thought. Every quasar we see could be connected to something much bigger, something beyond even the observable universe. This would mean that our search for the first quasars is not just a quest to understand the past, but also a journey into the deepest mysteries of existence itself. The more we learn, the more we realize that quasars are not just distant points of light. They are cosmic messages, telling us that the universe is far stranger than we ever imagined. And as we continue to uncover their secrets, we may find that the story of quasars is not just about how the universe began, but about what it will ultimately become. The search for the first quasars is not just about understanding how galaxies formed in the early universe, it's about unlocking the deepest secrets of space and time itself. These distant beacons are not just remnants of a bygone era. They are cosmic laboratories that reveal how the laws of physics operated when the universe was still young. But the more we study quasars, the more mysteries they seem to present. One of the biggest questions is how quasars formed so quickly after the Big Bang. To exist less than a billion years after the universe began, these supermassive black holes must have grown at an astonishing rate. But this presents a paradox. The process by which black holes grow, accreting matter from their surroundings, should take much longer. The standard models of black hole formation suggest that such massive objects should have taken billions of years to reach the sizes we observe in these early quasars. So how did they form so fast? One possibility is that the first black holes didn't form from the collapse of stars, as we see today, but instead originated from the direct collapse of massive gas clouds. In this scenario, instead of forming a star first and then collapsing into a black hole, some regions of the early universe may have been dense enough for entire clouds of gas to collapse directly into black holes. These direct collapse black holes could have started with masses tens of thousands of times greater than the Sun, allowing them to grow into supermassive black holes much faster than traditional models suggest. But even this idea has its challenges. For a direct collapse black hole to form, the gas cloud must avoid fragmenting into smaller stars. In the early universe, conditions may have been just right for this to happen, perhaps due to the lack of heavy elements, which affect how gas cools and collapses. However, this theory is still being tested, and astronomers continue to search for more clues. Another theory suggests that black holes could have grown rapidly through runaway collisions in dense star clusters. In the crowded conditions of the early universe, massive stars may have frequently collided, merging to form even bigger stars that collapsed into black holes. These growing black holes could then merge with one another, quickly reaching supermassive sizes. If this process occurred, it would mean that the early universe was a much more chaotic and violent place than we currently imagine. There is also a more exotic possibility, one that challenges the very nature of black holes themselves. Some physicists have proposed that the first quasars might not be powered by normal black holes at all, but instead by something even stranger. For example, primordial black holes, hypothetical black holes that formed in the very first moments of the universe, could have existed before the first stars were even born. If these primordial black holes merged and grew, they could have given rise to quasars much earlier than we would expect. Another radical idea suggests that what we think of as black holes might not actually be singularities surrounded by event horizons, but rather exotic objects like gravastars or fuzzballs. In some versions of quantum gravity, black holes might have more complex internal structures that allow them to grow in ways we don't yet understand. If these ideas are correct, then the quasars we observe might not just be massive black holes, they could be something entirely different, revealing new physics beyond our current theories. The search for the first quasars is also deeply connected to another fundamental mystery: dark matter. Astronomers know that galaxies, including those that host quasars, are surrounded by vast halos of invisible matter that does not emit light but exerts a gravitational influence. Some researchers believe that dark matter played a crucial role in the formation of the first quasars, acting as a gravitational scaffold that allowed gas to collapse more quickly and form supermassive black holes. But what if dark matter is not just a passive ingredient in galaxy formation? What if it directly interacts with black holes in ways we don't yet understand? Some theories propose that dark matter could accumulate around black holes, affecting their growth and the energy they release. If this is true, then studying quasars could provide new insights into the nature of dark matter itself, one of the greatest unsolved mysteries in physics. Then there's the question of what happens inside a quasar's accretion disk. The swirling disk of gas around a quasar's black hole is one of the most extreme environments in the universe. Temperatures reach millions of degrees, magnetic fields twist and snap, and matter is accelerated to near the speed of light. But despite decades of study, we still don't fully understand the physics of these disks. For example, how exactly does matter fall into a black hole? According to classical physics, material should spiral inward gradually, losing energy as it moves closer. But observations of quasars suggest that matter sometimes plunges in much more quickly than expected, as if some unknown force is pulling it in. Some researchers suspect that magnetic fields play a crucial role, acting like cosmic conveyor belts that channel material toward the black hole's event horizon. Others believe that quantum effects might be at play, altering how particles behave in these extreme conditions. There's also the mystery of why some quasars appear to turn on and off so quickly. In recent years, astronomers have discovered changing look quasars, objects that seem to switch between active and dormant states in just a few years. This is surprising because the traditional view of quasars suggests that their fueling processes should operate on much longer timescales. The sudden brightening or dimming of a quasar could mean that something unexpected is happening, such as abrupt changes in the accretion flow or even interactions with other massive objects. One of the most exciting developments in quasar research is the discovery of gravitational waves, ripples in space-time caused by massive cosmic events. If two supermassive black holes merge, they should create powerful gravitational waves that could be detected by instruments like LIGO and future space-based observatories. Some astronomers believe that studying quasars could help us find evidence of these mergers, providing a new way to probe the universe's most extreme events. And then there's the possibility that quasars might be linked to something even more mysterious: cosmic strings. These hypothetical objects are thought to be remnants of the early universe, thin filaments of energy stretching across space. Some theories suggest that if a cosmic string passed near a quasar, it could leave a detectable imprint on its light. If we were to find such an effect, it would provide direct evidence for physics beyond the standard model, potentially revealing new insights about the fundamental structure of the universe. Quasars also raise profound questions about the nature of time and the ultimate fate of the universe. If black holes can evaporate over time, then the supermassive black holes powering quasars might eventually disappear, leaving behind nothing but faint radiation. But what if, instead of vanishing, these black holes serve as seeds for the next phase of cosmic evolution? Some scientists speculate that in the distant future, black holes could become the dominant structures in the universe, with quasars representing a brief but crucial phase in this transition. Others propose that the energy released by quasars might influence the large-scale structure of the cosmos, shaping how matter is distributed across billions of light-years. Ultimately, the search for the first quasars is not just about finding the most distant objects in the universe. It's about understanding our place in the grand story of cosmic evolution. Each quasar we observe is a window into the past, a clue to the forces that shape the universe we see today. And as new telescopes like the James Webb Space Telescope continue to push the boundaries of discovery, we may find that the true nature of quasars is even stranger than we ever imagined. The deeper we look into the universe, the further back in time we see. And as we uncover more quasars from the early universe, we begin to realize that these cosmic beacons are not just relics of the past. They are active players in shaping the cosmos itself. The first quasars likely had a profound effect on their surroundings, influencing everything from the formation of galaxies to the distribution of matter on the largest scales. But how exactly did they shape the universe? And what can they tell us about the fundamental forces that govern reality? One of the most intriguing mysteries is how the first quasars contributed to the epoch of reionization, a crucial phase in the history of the universe. After the Big Bang, the universe was a dense, hot soup of particles. As it expanded and cooled, protons and electrons combined to form neutral hydrogen atoms, creating a universe that was dark and opaque. But at some point, this neutral hydrogen was reionized, meaning it was stripped of its electrons, making the universe transparent to light once again. This transition marks the beginning of the universe as we see it today, where galaxies, stars, and quasars shine brightly across vast cosmic distances. The problem is, we don't fully understand what caused this reionization. The leading theory is that the first stars and galaxies emitted enough high-energy radiation to ionize the surrounding hydrogen. But quasars are also powerful sources of extreme ultraviolet and X-ray radiation, meaning they could have played a major role in this process. If the first quasars were numerous and energetic enough, they could have accelerated reionization, reshaping the universe at large scales. But there's a catch: quasars are relatively rare compared to galaxies. While they emit enormous amounts of radiation, there may not have been enough of them to account for the entire reionization process. This leads to an even deeper mystery. Was there some other unknown source of high-energy radiation in the early universe? Could there have been an exotic mechanism we have yet to discover, one that fundamentally alters our understanding of cosmic evolution? The search for the first quasars is also intertwined with another enigma. Why do we find supermassive black holes in galaxies of all sizes? Traditionally, we think of quasars as being associated with massive galaxies, where vast amounts of gas can fuel their growth. But recent discoveries have shown that even small galaxies can host surprisingly massive black holes, challenging our understanding of how these objects form. If small galaxies in the early universe could host quasars, it could mean that supermassive black holes are more common than we thought, and that our models of galaxy evolution need to be revised. One possibility is that black holes and galaxies grew together from the very beginning. This idea, known as coevolution, suggests that as galaxies formed, their central black holes grew alongside them, influencing each other in a delicate balance. But this raises a paradox. How did this feedback mechanism emerge so early in the universe? Did black holes shape galaxies? Or did galaxies shape black holes? The answer to this question could revolutionize our understanding of cosmic history. Another perplexing discovery is the existence of ultraluminous quasars, objects so bright that they challenge our understanding of how much energy a black hole can release. Some of these quasars emit thousands of times more energy than an entire galaxy, making them among the most extreme objects in existence. The standard model suggests that this energy comes from material falling into the black hole, but there's a limit to how much matter a black hole can consume at once. When too much material piles up, it should create a pressure strong enough to push matter away, essentially starving the black hole of new fuel. So how are these ultraluminous quasars breaking this limit? One possibility is that they are accreting matter in a way we don't yet understand. Instead of a steady flow of gas, the material might be channeled into the black hole in bursts, allowing it to temporarily exceed its theoretical brightness. Another idea is that strong magnetic fields are playing a role, helping to funnel material into the black hole at extreme rates. But if this is true, it could mean that we are missing a crucial piece of the puzzle when it comes to how black holes behave. And then there's the strangest question of all: could quasars be hiding something even more mysterious? Some physicists have proposed that the light we see from quasars might not be coming from ordinary black holes, but from something far more exotic. There are theories that suggest black holes could be gateways to other dimensions, or that they might harbor remnants of an earlier universe. If these ideas are correct, then studying quasars could provide clues about the very fabric of reality, challenging everything we think we know about space and time. As telescopes become more powerful, we are pushing closer to the edge of the observable universe. The James Webb Space Telescope has already begun detecting galaxies from the earliest periods of cosmic history, and astronomers are eager to see if it can uncover even more distant quasars. If we can find quasars that existed just a few 100 million years after the Big Bang, we might finally answer some of the biggest questions in astrophysics. But there's always the possibility that new discoveries will create even bigger mysteries. The more we learn about the first quasars, the more we realize how much we still don't understand. Were these objects truly the first supermassive black holes, or were there even earlier generations that we have yet to detect? Could some of the first quasars be hiding behind thick clouds of gas and dust, invisible to our current telescopes? And most intriguingly, could there be entirely new forms of cosmic objects that we have yet to imagine? Quasars are more than just distant lights in the night sky. They are time machines, laboratories, and cosmic signposts that guide us toward the deepest truths of the universe. The search for the first quasars is not just about looking into the past, it's about understanding the forces that shaped everything we see today. And as we continue to explore the universe, we may find that the mysteries of quasars are just the beginning of an even greater cosmic journey. The search for the first quasars is far from over. Every new discovery brings more questions, forcing astronomers to rethink their assumptions about the early universe. One of the most pressing questions is, how did these quasars form so quickly? Supermassive black holes, which power quasars, take time to grow. The traditional view is that they form from the collapse of massive stars and gradually gain mass by pulling in surrounding gas. But the quasars we see in the early universe are already billions of times the mass of our Sun. That doesn't leave much time for them to grow under conventional models. This leads to an unsettling possibility. What if black holes didn't form the way we think they did? Instead of starting as the remnants of dead stars, could some black holes have formed directly from collapsing clouds of gas? This idea, known as direct collapse black hole formation, suggests that under the right conditions, a dense region of gas could collapse straight into a black hole without ever forming a star first. If this happened in the early universe, it could explain why we see supermassive black holes appearing so soon after the Big Bang. But this theory raises its own mysteries. Why would some gas clouds collapse directly into black holes while others formed stars and galaxies? And if direct collapse black holes existed, could some of them have grown even larger than the quasars we see today? There is even speculation that some of these ancient black holes might still be lurking in the universe, hidden in regions where we haven't looked yet. Another major puzzle surrounding quasars is their incredible brightness. The most luminous quasars emit thousands of times more energy than our entire Milky Way galaxy. This energy comes from matter falling into the black hole, heating up as it spirals inward. But there's a theoretical limit to how much a black hole can feed. When too much material piles up, radiation pressure should push new matter away, effectively starving the black hole. Yet, some quasars appear to be breaking this limit, growing at rates that should be impossible. One possible explanation is that these quasars are accreting matter in ways we don't yet understand. Instead of a smooth, steady flow of gas, the material might be getting funneled in bursts, allowing the black hole to temporarily exceed its theoretical feeding limit. Another theory is that strong magnetic fields are playing a role, helping direct material into the black hole at extreme rates. If this is true, it could mean that black holes are even more complex than we thought. The search for the first quasars is also revealing unexpected connections between black holes and galaxy formation. Traditionally, we think of quasars as rare, extreme objects found in the hearts of massive galaxies. But recent observations suggest that supermassive black holes might be far more common than we assumed. Some small, faint galaxies appear to host surprisingly massive black holes, challenging our understanding of how galaxies and black holes grow together. This leads to an even deeper question: did black holes shape galaxies? Or did galaxies shape black holes? Some scientists believe that as galaxies formed, their central black holes grew alongside them, regulating star formation through powerful winds and jets. Others suggest that black holes came first, acting as seeds around which galaxies formed. The truth may be a combination of both ideas, but we still don't fully understand the relationship. And then there's the biggest mystery of all: could some quasars be hiding something even more exotic? Some physicists have proposed that the light we see from quasars might not be coming from ordinary black holes, but from something far stranger. There are theories suggesting that quasars could be powered by exotic forms of matter, like primordial black holes from the early universe or even objects that defy our current understanding of physics. One particularly radical idea is that some quasars might be wormholes, gateways to other parts of the universe, or even other dimensions. While this might sound like science fiction, certain models of quantum gravity allow for the existence of stable wormholes. If quasars were actually wormholes, their strange properties, such as their extreme brightness and rapid variability, could make more sense. But proving this idea would be incredibly difficult, requiring entirely new types of observations and experiments. With new telescopes like the James Webb Space Telescope, we are pushing closer to the edge of the observable universe. Already, JWST has begun detecting galaxies and quasars from the earliest periods of cosmic history. If we can find quasars that existed just a few 100 million years after the Big Bang, we might finally answer some of the biggest questions in astrophysics. But as history has shown, every new discovery tends to raise more questions than it answers. The more we learn about the first quasars, the more we realize how much we still don't understand. Were these objects truly the first supermassive black holes, or were there even earlier generations that we have yet to detect? Could some of the first quasars be hidden behind thick clouds of gas and dust, invisible to our current telescopes? And most intriguingly, could there be entirely new kinds of cosmic objects waiting to be discovered? Quasars are more than just distant lights in the night sky. They are time machines, laboratories, and cosmic signposts that guide us toward the deepest truths of the universe. The search for the first quasars is not just about looking into the past, it's about understanding the forces that shaped everything we see today. And as we continue to explore the universe, we may find that the mysteries of quasars are just the beginning of an even greater cosmic journey. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.